Welcome back. Tonight, we settle in with the slow, patient work of astronomers who climbed above the clouds to build their temples of glass and iron on remote peaks, where the air grew thin and the seeing grew steady, from the mule trails winding up Mount Hamilton in the 1880s to the careful grinding of the Great Mirror at Palomar. We will trace how these observatories, perched in silence far from city lights, gradually revealed the true scale of the universe around us. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. In the middle decades of the 19th century, when most serious astronomical work was conducted from observatory domes nestled comfortably within the grounds of ancient universities or positioned conveniently near the homes of wealthy amateur enthusiasts, a small number of particularly thoughtful individuals began to wonder whether the very air above their heads might be obscuring the celestial wonders they so patiently studied. These pioneers of altitude, as we might gently call them, were not reckless adventurers seeking thrills in high places, but rather careful scientists who had noticed, through years of quiet observation, that the atmosphere itself presented a kind of veil between their instruments and the stars. Their story unfolds slowly, as all good scientific stories do, across decades of patient effort and occasional disappointment, and it begins perhaps most notably with a Scottish astronomer who decided, in the year 1856, to carry his telescopes up the slopes of a volcanic island in the Atlantic Ocean. Charles Piazzi Smith was born in 1819 in Naples, where his father served as a naval officer, and he received his rather distinctive middle name in honor of the Italian astronomer Giuseppe Piazzi, who had discovered the first asteroid, Ceres, at the very beginning of that century. By the time Smith reached his late 30s, he had already served for more than a decade as the Astronomer Royal for Scotland, a position of considerable respectability that provided him with ample opportunity to contemplate the shortcomings of astronomical observation from the lowlands. Edinburgh, where his observatory stood, suffered from the same difficulties that plagued all northern European observatories of that era, namely the frequent presence of clouds, the shimmering distortion caused by heat rising from the ground, and the general haziness that seemed to worsen as cities grew larger and burned more coal. Smith had read with interest the scattered reports from earlier observers who had noted that stars appeared steadier when viewed from elevated locations, and he conceived a plan to test this notion systematically by transporting proper scientific instruments to a genuinely high altitude and conducting careful measurements over an extended period. The destination Smith chose for his expedition was the island of Tenerife, the largest of the Canary Islands, which rises from the Atlantic Ocean some 200 miles off the coast of northwestern Africa. At the island's center stands the volcanic peak of El Teide, reaching to more than 12,000 feet above the sea, but Smith established his primary observing station at a somewhat lower elevation on a ridge called Guajira, at approximately 8,900 feet, where the terrain was more suitable for setting up delicate equipment, and where he and his small party could survive with reasonable comfort for the several weeks their observations would require. He also maintained a secondary station at a lower elevation, around 7,000 feet, which allowed him to compare the quality of observations made at different altitudes under otherwise similar conditions. The expedition of 1856 was funded in part by the British Admiralty, which maintained a general interest in astronomical matters for purposes of navigation, and Smith brought with him an assortment of telescopes, spectroscopes, and other instruments, along with his wife Jessie, who assisted with the work and proved herself an intrepid traveler in her own right. The observations Smith conducted during those weeks on Tenerife produced results that were, to the careful reader of his subsequent reports, quietly remarkable. He documented with methodical precision the improvement in what astronomers would later term seeing, which refers to the steadiness of the air and the sharpness of images produced by a telescope. At lower elevations, even on clear nights, the images of stars tend to shimmer and dance about, a phenomenon caused by turbulence in the atmosphere as layers of air at different temperatures mix and swirl above the observer. At Guajara, Smith found that this shimmering was substantially reduced, allowing finer details to be observed and more precise measurements to be taken. He also noted the reduction in the general haziness of the sky and the deeper darkness between the stars, both consequences of looking through a thinner layer of atmosphere. His measurements of the solar spectrum, conducted with a device called a spectroscope that spread the sun's light into its component colors, revealed that certain dark lines in that spectrum, which were known to be caused by absorption in the Earth's atmosphere rather than in the sun itself, were noticeably weaker when observed from the mountaintop. This finding provided direct evidence that the atmosphere was absorbing and scattering a significant portion of the light from celestial objects before it could reach telescopes at sea level. Upon his return to Scotland, Smith published his findings in a substantial volume and advocated energetically for the establishment of permanent high-altitude observatories, arguing that the advantages he had documented would more than repay the inconveniences and expenses involved. The reception his proposals received from the broader astronomical community was, however, rather cooler than he had hoped. Many established astronomers, particularly those at the venerable institutions of Europe, expressed polite skepticism about the necessity of relocating to remote and uncomfortable mountaintops. These scholars had built their careers and their reputations at observatories situated near great universities, where they enjoyed the companionship of fellow intellectuals, access to well-stocked libraries, and the various amenities of civilized urban life. They pointed out, not unreasonably, that the construction and staffing of observatories in such distant locations would present formidable logistical challenges, and they questioned whether the improvements in seeing that Smith reported would truly justify the considerable difficulties involved. Some suggested that advances in telescope design and the refinement of observing techniques might achieve comparable improvements without requiring astronomers to exile themselves to volcanic islands or other inhospitable locations. This institutional conservatism, while understandable from a practical standpoint, would gradually yield over the following decades as more evidence accumulated and as a new generation of astronomers, particularly in the United States, began to demonstrate what could be accomplished from high places. The story of American mountaintop astronomy begins, in a certain sense, with the peculiar ambitions of a man named James Lick, who had accumulated a considerable fortune through various business ventures in San Francisco during and after the California Gold Rush. Lick was born in 1896 in Pennsylvania, worked for many years as a piano maker in South America, and arrived in California in 1848, just 17 days before gold was discovered at Sutter's Mill, carrying with him a substantial sum of money and an acute sense for real estate investment. By the time he reached his 70s, Lick had become one of the wealthiest men in California, and he began to contemplate how his fortune might best be used to create a lasting monument to his name. His initial ideas tended toward the grandiose and somewhat eccentric, including at one point a plan to construct an enormous pyramid in his own honor somewhere in San Francisco. When astronomical enthusiasts and scientific advisors gradually persuaded him that a great telescope might serve as a more dignified and useful memorial, Lick agreed, though he initially insisted that this instrument should be placed directly above his own grave, wherever that might be located. This notion presented obvious practical difficulties, and it required considerable diplomatic effort on the part of his advisors to convince him that a telescope of the size he envisioned would function far better atop a mountain than in a cemetery. In 1874, Lick signed a deed of trust allocating $700,000 for the construction of a telescope superior to any then in existence, to be presented upon completion to the University of California. The site eventually selected for this instrument was Mount Hamilton, a peak of approximately 4,300 feet situated to the east of San Jose, which offered reasonably good atmospheric conditions and was accessible, with considerable effort, from the populated areas of the San Francisco Bay. Lick himself died in 1876, before construction was completed, and his remains were eventually interred beneath the pier supporting the great telescope he had funded, thus fulfilling in a modified form his wish to rest beneath his monument. The Lick Observatory, as it came to be known, was formally transferred to the University of California in 1888, equipped with a 36-inch refracting telescope that was indeed, at that moment, the largest in the world. The first director appointed to oversee this new institution was Edward Singleton Holden, a man of considerable astronomical accomplishment and administrative energy who had previously served at the United States Naval Observatory and at the University of Wisconsin. Holden took up his position at Lick in 1888 and immediately set about establishing the observatory as a center for serious research, recruiting talented astronomers and instituting programs of systematic observation. His tenure was not without difficulties, as the isolation of the Mountaintop location created tensions among the staff and as Holden's own management style generated friction with some of his colleagues. But the observatory under his direction produced important work and demonstrated convincingly that first-rate astronomical research could indeed be conducted from such remote elevations. The success of Lick Observatory provided a powerful example that would influence the planning of subsequent American observatories and help to shift the center of gravity of serious astronomical research away from the traditional European institutions. Among the astronomers who took inspiration from these developments was William Henry Pickering, a younger brother of the more famous Edward Charles Pickering who directed the Harvard College Observatory. William Pickering possessed an adventurous temperament and a particular interest in planetary observation, and he became convinced that even higher and more favorable sites might be found in other parts of the world. In 1891, he established a temporary observing station at Arequipa, in the southern highlands of Peru, at an elevation of approximately 8,060 feet. This station, operated as an outpost of the Harvard Observatory, was intended primarily for photographic surveys of the southern sky, which could not be observed from the northern hemisphere, but it also provided Pickering with opportunities to evaluate the seeing conditions at this high-altitude tropical location. The Arequipa station operated for many years and contributed valuable data to various astronomical programs, though Pickering's own observations were sometimes criticized by his peers for lack of rigor, and some of his more speculative claims regarding features on the surfaces of the Moon and Mars did not withstand later scrutiny. The scientific rationale for seeking out high-altitude observing sites had by now become reasonably well established among progressive astronomers, even if some of the older generation remained unconvinced. The benefits could be grouped into several related categories, each of which made a meaningful contribution to the quality of observations. First and most obvious was the matter of atmospheric absorption, the simple fact that the Earth's atmosphere blocks or weakens certain wavelengths of light before they can reach the ground. By positioning a telescope at a higher elevation, one reduced the total thickness of atmosphere through which the light must pass, thereby allowing more of that light to reach the instrument. This advantage was particularly significant for observations in the infrared and ultraviolet portions of the spectrum, where atmospheric absorption was most severe, but it provided measurable benefits across all wavelengths. Second was the improvement in seeing that Smith had documented so carefully: the reduction of atmospheric turbulence that caused star images to shimmer and blur. The most troublesome turbulence tended to occur in the lower atmosphere, where heating from the ground created rising currents of warm air that mixed with cooler air above. And by ascending above this turbulent layer, astronomers could obtain significantly sharper images. Third was the matter of sky darkness, the reduction of scattered light from artificial sources and from the atmosphere itself that made the sky between stars appear not truly black but faintly luminous. High mountaintops, located far from cities and above much of the atmospheric dust and moisture that scattered light, offered skies of a deeper darkness that allowed fainter objects to be detected and studied. No account of the pioneers of altitude would be complete without mention of George Ellery Hale, who emerged in the final years of the 19th century as perhaps the most influential figure in the planning and funding of large American telescopes. Hale was born in 1868 in Chicago, the son of a prosperous elevator manufacturer, and he developed a passion for astronomy at an early age, building small telescopes and observing the sun from a homemade observatory in his family's backyard. His scientific interests focused primarily on solar physics, but his administrative and fundraising abilities proved equally remarkable, and he possessed an extraordinary gift for convincing wealthy individuals to part with substantial sums of money in support of astronomical research. Hale understood intuitively that the construction of great telescopes required not only scientific vision but also the cultivation of personal relationships with potential donors, and he pursued this work with an energy and charm that few of his colleagues could match. His efforts would eventually result in the funding of several of the most important observatories of the 20th century, and his influence on the geographic and institutional landscape of American astronomy cannot be overstated. As the 19th century drew toward its close, the foundations had been laid for what would become a remarkable era of mountaintop observatory construction, driven by the insights of these early visionaries who had looked upward at the stars and understood that to see them more clearly, one must first climb closer to the sky. And now we turn our attention to a mountain in California, where in the latter decades of the 19th century, a most remarkable undertaking was beginning to take shape, an endeavor that would eventually place one of the world's finest telescopes atop a peak that had previously known only the quiet company of oak trees and the occasional passing of mule deer through its grassy meadows. Mount Hamilton rises to an elevation of 4,209 feet above sea level, situated in the Diablo Range to the east of San Jose, and in the 1870s this was considered quite remote territory indeed, accessible only by rough trails that wound their way through the golden hills of what was then a predominantly agricultural region. The mountain takes its name from the Reverend Laurentine Hamilton, who had climbed to its summit in 1861, though he could scarcely have imagined that within a few decades this same peak would become home to one of the most sophisticated scientific instruments ever constructed by human hands. The story of how an observatory came to be built in such an isolated location begins with a man named James Lick, who had accumulated considerable wealth through real estate investments in San Francisco during the years following the gold rush. Lick was a piano maker by original trade, having learned the craft in his native Pennsylvania before traveling to South America and eventually settling in California just weeks before gold was discovered at Sutter's Mill in 1848. By the time he began contemplating how to dispose of his fortune, he was one of the wealthiest men in the state, and his thoughts turned toward leaving behind something of lasting significance, something that might benefit humanity and preserve his name for generations yet unborn. After considering various philanthropic possibilities, including at one point a grand pyramid larger than the Great Pyramid of Giza to be constructed in his honor in downtown San Francisco, Lick was eventually persuaded by astronomers and scientific advisors that a great telescope would serve as a more fitting and useful memorial. The deed of trust establishing what would become Lick Observatory was signed in 1874, and work began in earnest on what would prove to be one of the most challenging construction projects in California's young history. Before any telescope could be installed, a road had to be built, for no road existed that could carry the heavy equipment and building materials required for such an ambitious undertaking. The construction of this road began in 1876 and would not be completed until 1887, more than a decade of patient labor winding a path up the mountain's flanks. This was the first county road in the United States built specifically to serve an astronomical observatory, a distinction that speaks to the unprecedented nature of the entire enterprise. The road stretched for approximately 26 miles from the Santa Clara Valley floor to the summit, climbing through switchback after switchback, each curve carefully graded so that wagons laden with bricks and lumber, and eventually the precious optical components, could make the journey without mishap. The grade of the road was kept to a gentle 6.5% or less along its entire length, a specification that required considerable engineering ingenuity given the rugged terrain through which it passed. Workers carved the roadbed from hillsides of serpentine and sandstone, filled ravines, and constructed wooden bridges over seasonal creeks that would swell with winter rains. The total cost of the road alone approached $70,000, a substantial sum in that era, and it employed crews of laborers who lived in temporary camps along the route as they slowly extended the thoroughfare toward the summit. Meanwhile, far away in Massachusetts, the firm of Alvin Clark and Sons was undertaking the meticulous work of grinding and polishing the great lens that would serve as the observatory's principal instrument. Alvin Clark was by then the most celebrated telescope maker in America, and his sons Alvin Graham Clark and George Bassett Clark carried on the family tradition of optical excellence. The lens they were creating for Mount Hamilton would measure 36 inches in diameter, making it upon completion the largest refracting telescope in the world, surpassing the 26-inch refractor at the United States Naval Observatory in Washington and the 27-inch refractor at the Vienna Observatory. The objective lens of a great refractor is actually composed of two separate elements, a crown glass component and a flint glass component, carefully figured and matched to minimize the chromatic aberration that would otherwise cause different colors of light to focus at different points. The glass blanks for the Lick telescope were cast by the firm of File-Mantois in Paris, and each weighed several hundred pounds. These precious discs of optical glass were then shipped across the Atlantic and overland to the Clark workshop in Cambridgeport, where the long process of grinding began. The grinding of a telescope lens is an undertaking that cannot be hurried, for the optical surface must be shaped to tolerances measured in fractions of a wavelength of light, and any attempt to rush the process invites the introduction of errors that would compromise the instrument's performance. Month after month, the Clark brothers worked at their grinding machines, testing the surfaces with interferometric methods, correcting minute irregularities, and gradually bringing the curves of each element toward their theoretical ideals. The completed lens would have a focal length of 57 feet, requiring a telescope tube of corresponding length and a dome large enough to house and rotate this considerable apparatus. James Lick himself did not live to see his telescope completed. He passed away in October of 1876, just as construction of the mountain road was getting properly underway. However, he had left detailed instructions regarding his final resting place, and in accordance with his wishes, his remains were initially interred in San Francisco's Masonic Cemetery. Then, In January of 1887, with the observatory buildings nearing completion and the great telescopes soon to be installed, James Lick's body was exhumed and transported up the newly finished road to Mount Hamilton, where it was placed in a tomb beneath the pier that would support the great refractor. There his remains lie still, directly beneath the instrument that bears his name, a circumstance that lends a certain contemplative quality to the midnight hours when astronomers guide the telescope across the heavens above their benefactor's eternal rest. The great Lick refractor saw first light in 1888 and immediately demonstrated the soundness of its construction and the excellence of its optics. The clarity of the mountain air, far above the dust and moisture of the valley below, combined with the precision of the Clark lens to produce images of celestial objects that exceeded what had been achieved at lower elevation observatories troubled by atmospheric turbulence. The observatory quickly attracted astronomers of exceptional ability, men who were willing to accept the isolation of mountain life in exchange for access to this magnificent instrument. Among those who came to work at Lick Observatory was Shuburn Wesley Burnham, a court reporter from Chicago who had developed a passionate interest in double stars, those pairs of suns that orbit around their common center of gravity and appear through the telescope as 2 points of light in close proximity. Burnham possessed extraordinarily keen eyesight and had already discovered hundreds of previously unknown double stars using a 6-inch telescope in his spare time. At Mount Hamilton, with the power of the 36-inch refractor at his disposal, he was able to resolve stellar pairs that had appeared as single points of light in smaller instruments and to add substantially to the catalogue of known binary systems. Double star astronomy may seem to the uninitiated a rather specialized pursuit, but the measurement of these systems provides crucial information about stellar masses. For when the orbital period and separation of a binary pair can be determined, the laws of celestial mechanics allow the combined mass of the two stars to be calculated. Burnham's careful observations and measurements, compiled over years of patient work, contributed significantly to our understanding of how stars are distributed in space and how they are related to one another through gravitational bonds that span the light years. Another astronomer whose work at Lick Observatory would prove of lasting importance was James Edward Keeler, who specialized in spectroscopy, the analysis of light that has been spread into its component colors by a prism or diffraction grating. In 1895, Keeler turned the spectroscope toward the rings of Saturn, those ethereal bands that had puzzled observers since Galileo first glimpsed them through his primitive telescope in 1610. The question of what the rings were made of had been debated for more than 2 centuries, with some theorists proposing that they were solid disks, others suggesting they might be liquid, and still others arguing that they must consist of innumerable small particles, each orbiting Saturn independently. Keeler's spectroscopic observations settled the matter definitively. By examining the Doppler shift in the light reflected from different portions of the rings, he was able to show that the inner edge of the ring system was moving faster than the outer edge, precisely as would be expected if the rings consisted of independent particles, each following its own orbit around the planet in accordance with Kepler's laws. A solid ring would rotate as a unit, with its outer edge necessarily moving faster than its inner edge to complete each rotation in the same time. The observed velocity distribution was inconsistent with a solid structure and perfectly consistent with a vast swarm of particles, each a tiny moon in its own right. This elegant application of spectroscopic technique to a long-standing astronomical puzzle demonstrated the power of the new methods that were transforming observational astronomy in the closing years of the 19th century. Edward Emerson Barnard was another astronomer whose achievements at Lick Observatory would secure his place in the history of the science. Barnard had come to astronomy from humble beginnings in Tennessee, where he had worked as a photographer's assistant before his observational talents brought him to the attention of the astronomical community. His eyesight was legendary, and his patience at the telescope was inexhaustible. In September of 1892, Barnard was examining the region near Jupiter when he noticed a tiny point of light that was not recorded on any star chart. Careful observation over subsequent nights confirmed that this faint object was moving in concert with Jupiter, maintaining its position relative to the giant planet as both progressed along their orbits around the Sun. What Barnard had discovered was Jupiter's fifth moon, a small body now known as Amalthea, orbiting closer to the planet than any of the four large moons that Galileo had observed nearly 3 centuries earlier. This was the first satellite of Jupiter discovered since Galileo's time, and it would prove to be the last moon of any planet to be discovered through direct visual observation rather than through photography. Subsequent discoveries of planetary satellites would all be made on photographic plates, where the longer exposures possible with the camera could reveal objects too faint for the human eye to perceive, even when aided by the largest telescopes. Barnard's discovery thus marks a kind of ending, the final achievement of a tradition of visual observation that stretched back to the dawn of telescopic astronomy. Life on Mount Hamilton for the astronomers and their families was marked by considerable hardship, particularly during the winter months when storms could sweep across the summit and leave the community isolated for days or even weeks at a time. The road that had been so laboriously constructed was susceptible to washouts and mudslides during heavy rains, and snow could make passage impossible until crews could clear the way. Provisions had to be stockpiled against these periods of isolation, and the small community atop the mountain developed something of the character of a frontier settlement, self-reliant by necessity. Families lived in cottages clustered near the observatory buildings, and children were educated in a one-room schoolhouse where a single teacher served all grades. The wives of astronomers managed households under conditions quite unlike those their counterparts in cities enjoyed, with limited access to shops and services and long periods when their husbands worked through the night and slept through much of the day. The social world available to these mountain dwellers was confined to their immediate neighbors, the same faces seen day after day, the same conversations renewed across kitchen tables and at community gatherings. And yet there was also a certain beauty to this isolation, a quietude that allowed for contemplation and close observation of the natural world beyond the observatory dome. The meadows around the summit bloomed with wildflowers in spring, and the clear mountain air afforded views across the Santa Clara Valley to the distant ridges of the Coast Range. At night, when the astronomers were at work in the dome, the families in their cottages could look up at the same stars being studied through the great refractor, those ancient points of light that had drawn human wonder since the first hominids gazed upward from the African savanna. The work continued, night after night, season after season, as the observers at Mount Hamilton added their increments of knowledge to humanity's understanding of the cosmos, each measurement and each discovery building upon what had come before and preparing the foundation for what would follow. In the final years of the 19th century, in a small village in Wisconsin where the winters brought heavy snows and the summers hummed with insects from the nearby lake, there arose a building of such grandeur and scientific ambition that it seemed almost misplaced among the dairy farms and quiet country roads. This was Yerkes Observatory, and its story begins with a young man named George Ellery Hale, who possessed an unusual combination of scientific brilliance and persuasive charm, and who would spend his life convincing wealthy men to build ever larger telescopes for the advancement of human understanding. Hale was barely 24 years old when he began dreaming of this observatory, and he was driven by a conviction that the universe could be understood through careful observation and patient measurement, that the stars held secrets which would yield themselves to those who looked long and carefully enough. George Ellery Hale had grown up in Chicago, the son of a wealthy elevator manufacturer who indulged his son's fascination with astronomy by building him a small observatory on the family property. From this modest beginning, Hale developed an appetite for larger instruments and grander projects that would define his entire career. He understood, perhaps better than any scientist of his generation, that great observatories required not only scientific vision but also substantial funding, and that such funding must come from those who had accumulated fortunes in the rapidly industrializing American economy. This understanding led him, in the early 1890s, to approach one of Chicago's most controversial figures, a man whose name was spoken in some circles with admiration and in others with considerable disdain. Charles Tyson Yerkes had made his fortune in the streetcar business, acquiring and consolidating the various transit lines that moved people through the crowded streets of Chicago. He was a man of considerable financial acumen and equally considerable moral flexibility, having served time in prison earlier in his life for misappropriating public funds during his days as a Philadelphia banker. His methods in Chicago were aggressive and often ethically questionable, involving complex financial arrangements that enriched him while leaving the city with aging equipment and overcrowded cars. The newspapers regularly criticized him, and polite society regarded him with suspicion even as they accepted his money for various charitable causes. Yerkes understood that his reputation needed repair, and he was searching for a project that might cast him in a more favorable light, something grand and public-spirited that would associate his name with the advancement of knowledge rather than the accumulation of wealth through dubious means. Hale recognized in Yerkes both an opportunity and a willing participant in a kind of transaction that benefited both parties. The young astronomer wanted to build the largest refracting telescope in the world, surpassing the 36-inch instrument at Lick Observatory in California, and he needed someone with both the means and the motivation to fund such an ambitious undertaking. Yerkes, for his part, saw in Hale's proposal a chance to attach his name to something permanent and respectable, an institution that would outlast the controversies of his business career and perhaps reshape how future generations remembered him. The negotiation between them was not without its difficulties, as Yerkes repeatedly attempted to reduce his commitment or attach conditions that Hale found unacceptable. But in the end, the streetcar magnate provided the funds necessary to construct both the great telescope and the building that would house it. The telescope itself was to be a refractor, which is to say an instrument that gathers and focuses light through lenses rather than mirrors. The objective lens, that large piece of glass at the front of the telescope through which starlight first enters, would measure 40 inches in diameter, making it the largest such lens ever produced. This task fell to the firm of Alvan Clark & Sons, a family of optical craftsmen in Massachusetts who had established themselves as the finest makers of astronomical lenses in the world. The elder Alvan Clark had died in 1887, but his son Alvan Graham Clark continued the family tradition, and it was he who undertook the grinding and figuring of the great Yerkes lens. The work required years of painstaking effort, as the glass blank had to be carefully shaped to focus light from distant stars to a single precise point, with any imperfection in the curve causing the resulting images to blur or distort. The completed lens weighed approximately 500 pounds and represented the practical limit of what could be achieved with refracting telescope technology. A lens, unlike a mirror, can only be supported around its edges, and as the diameter increases, the weight of the glass causes it to sag and flex under its own mass, distorting the very optical surface that has been so carefully figured. The 40-inch lens at Yerkes pushed against this fundamental physical constraint, and larger refractors have never been seriously attempted since, making this instrument not merely the largest of its era, but the largest that will likely ever exist. To house this enormous telescope, Hale engaged the architect Henry Ives Cobb, who designed a building that drew upon the Romanesque Revival style, then popular for institutional buildings in America. The observatory that Cobb created resembles nothing so much as a medieval fortress or monastery, with its heavy stone walls, rounded arches, and fortress-like towers. The brown brick and terracotta ornamentation give the structure a warm, substantial appearance, and the building stretches across the landscape with a confident permanence that suggests the long-term nature of astronomical research. 3 domes rise from the structure, the largest being the great 90-foot dome that shelters the 40-inch refractor, with smaller domes housing additional instruments at either end of the building. There is something almost defiant about the architecture, as if Cobb wished to assert that the pursuit of knowledge deserved the same monumental treatment that previous centuries had reserved for cathedrals and palaces. The practical challenges of operating such a large instrument within this building were considerable, and the solutions devised by the engineers reveal the inventiveness that characterized this era of observatory construction. The telescope tube itself measured 63 feet in length, and when pointed toward objects near the horizon, the eyepiece where the observer worked could be raised some 70 feet above the floor. Simply reaching this eyepiece presented a significant problem, solved not by ladders or platforms that the observer would climb, but by a floor that could itself be raised and lowered. The entire floor of the dome room, some 75 feet in diameter, was mounted on hydraulic lifts that could elevate it by 23 feet, rising smoothly and quietly to bring the astronomer to whatever height the telescope's position required. This elevator floor was a marvel of engineering when it was installed, and it remains functional today, lifting visitors and researchers alike to meet the eyepiece wherever the great tube happens to be pointing. The observatory opened formally in October of 1897, with ceremonies that brought dignitaries and scientists from across the country to the small village of Williams Bay. Charles Yerkes attended and basked in the attention, though his reputation would never fully recover from the years of controversy, and he would die in New York in 1905, largely forgotten except for the observatory that bears his name. Hale became the first director, and under his leadership, the observatory attracted talented researchers and established itself as a leading center for astrophysical research, which is to say the application of physics to understanding the nature and composition of celestial objects rather than merely cataloging their positions. Among the astronomers who worked at Yerkes during its early years was Edwin Brant Frost, who would eventually succeed Hale as director and lead the observatory for more than 3 decades. Frost specialized in stellar spectroscopy, the careful analysis of starlight that has been spread into its component colors by a prism or grating. When light from a star passes through such a device, it produces a rainbow-like spectrum crossed by dark lines, and these lines reveal which chemical elements are present in the star's atmosphere. Each element absorbs light at specific wavelengths, leaving its own distinctive pattern of dark lines, and by measuring these patterns, astronomers can determine what distant stars are made of without ever visiting them. Frost catalogued the spectra of thousands of stars, measuring the slight shifts in spectral lines that indicate whether a star is moving toward or away from Earth, building up a picture of the motions and compositions of stars throughout our region of the galaxy. Another significant figure in the early history of Yerkes was Frank Schlesinger, who developed and refined techniques for measuring the distances to stars through photographic parallax. Parallax is the apparent shift in a nearby object's position when viewed from different locations, and for stars, astronomers can use Earth's orbit around the Sun to provide the different viewpoints. by photographing a star field in January, when Earth is on one side of its orbit, and again in July, when Earth has moved to the opposite side. Astronomers can detect the tiny shift in position of nearby stars against the background of more distant ones. This shift is extremely small, measured in fractions of an arc-second, and earlier attempts to measure stellar parallax had relied on visual observations that were limited by human perception and the vagaries of atmospheric conditions. Schlesinger recognized that photographic plates could record star positions with greater precision and consistency than the human eye, and he developed meticulous techniques for measuring these plates that dramatically improved the accuracy of stellar distance determinations. His work at Yerkes laid the foundation for the systematic measurement of stellar distances that would occupy astronomers for decades to come. Despite these scientific successes, Hale grew increasingly frustrated with the limitations imposed by the Wisconsin climate. The winters were bitterly cold, making observing uncomfortable and sometimes impossible, and the summers brought haze and humidity that degraded the clarity of the images. More fundamentally, Hale was already dreaming of larger telescopes, and he understood that a reflector using mirrors rather than lenses could be made much larger than any refractor. Such instruments would require the clearest possible skies and the most stable atmospheric conditions, and these were not to be found in the American Midwest. His thoughts turned increasingly toward California, where the mountains offered dark skies, dry air, and the steady atmospheric conditions that astronomers call good seeing. Within a few years of Yerkes opening, Hale had already begun planning what would become Mount Wilson Observatory, and though he remained nominally connected to Yerkes, his attention and energy were drawn increasingly westward. In 1915, an event occurred at Yerkes that connected this remote Wisconsin observatory to the most profound revolution in physics since Newton. Albert Einstein, then a professor in Berlin and not yet the worldwide celebrity he would become, visited the United States and made a stop at Williams Bay to discuss his work with the astronomers there. Einstein had recently completed his general theory of relativity, which reimagined gravity not as a force acting across empty space but as a curvature in the fabric of spacetime itself caused by the presence of mass. This theory made specific predictions that could be tested by astronomical observations, including the precise amount by which starlight should bend as it passes near the Sun. The astronomers at Yerkes listened as Einstein explained his ideas, engaging in the kind of collegial exchange of knowledge that has always characterized scientific communities at their best. Though the visit was brief and left few formal records, it represents a moment when the theoretical and observational branches of astronomy came together, each informing and inspiring the other. The years that followed would see Yerkes continue as an active research institution, though it never again commanded the central place in American astronomy that it held during its first decade. Larger telescopes on better sites gradually drew the most ambitious observational programs westward, and the 40-inch refractor, once the largest eye on the universe, became a historical treasure rather than a cutting-edge instrument. Edwin Frost continued as director until 1932. Despite progressive blindness that eventually left him unable to observe at all, a poignant circumstance for a man who had devoted his life to studying light from distant stars. The observatory at Williams Bay still stands today, its Romanesque towers rising above the trees near the shores of Geneva Lake, and the great refractor still points toward the heavens on clear nights, much as it did when George Ellery Hale first saw starlight through its lens more than a century ago. The floor still rises on its hydraulic lifts, and the dome still rotates to follow the motion of the sky, and visitors can still experience something of the wonder that the early astronomers must have felt when they first turned this magnificent instrument toward the stars. The mountains of Southern California rise from the coastal plains in long, gentle folds, and among these ranges the San Gabriel Mountains stand with particular quiet dignity, their peaks reaching toward the clear skies that drew astronomers to this region in the final years of the 19th century. Mount Wilson, named for Benjamin Wilson, a former mayor of Los Angeles who had cut a trail to its summit in 1864, would become one of the most significant sites in the entire history of astronomical observation, though in those early years it appeared to visitors as simply another chaparral-covered summit, fragrant with sage and California lilac, where the air grew thin and cool and the lights of the growing city below seemed very far away indeed. George Ellery Hale had already established himself as a solar astronomer of considerable reputation before he turned his attention to this particular mountain. He had built the Kenwood Observatory in Chicago as a young man, had directed the Yerkes Observatory in Wisconsin with its great 40-inch refractor, and had throughout these years maintained a singular focus on understanding the nature of our nearest star. Hale possessed what might be called a productive restlessness, an inability to remain satisfied with existing instruments when he could imagine better ones, and this quality, which served astronomy so well, would exact from him a considerable personal cost over the decades to come. In 1903, he made his first visits to Mount Wilson, climbing the rough trail to assess the seeing conditions, and what he found there convinced him that this summit offered something exceptional, a steadiness of air and a clarity of sky that surpassed what he had known in the flatlands of the Midwest. The establishment of Mount Wilson Observatory proceeded with a swiftness that reflected both Hale's determination and his remarkable ability to secure funding from wealthy benefactors. The Carnegie Institution of Washington, founded only recently with Andrew Carnegie's enormous gift for the advancement of scientific research, agreed to support Hale's vision for a solar observatory on the mountain, and by 1904 the work of construction had begun in earnest. One must picture the difficulty of this enterprise, for Mount Wilson rises to nearly 6,000 feet above sea level, and in those years no road reached its summit. Everything required for the observatory, every piece of scientific equipment, every beam and bolt and pane of glass, every provision for the workers who labored there, had to be carried up the mountain by mule trains that wound slowly along the narrow trail, the animals picking their careful way around switchbacks while laden with burdens that sometimes seemed impossible for such transport. The first major instrument to reach the summit was the Snow Horizontal Solar Telescope, a curious and ingenious device that had been designed for the Yerkes Observatory and was now dismantled and carried piece by piece up the mountain trail. This telescope, named for Helen Snow, whose bequest had funded its construction, employed a solostat, which is a mirror system that tracks the sun across the sky and directs its light along a fixed horizontal path into the observing chamber. The Snow telescope began operations in 1905, and with it Hale and his colleagues could study the solar spectrum in unprecedented detail, spreading the light of the sun into its component wavelengths and reading there the signatures of the elements that compose our star. The horizontal arrangement, however, proved to have certain disadvantages, for the long path of the light beam passed through layers of air near the ground that were warmed unevenly by the sun, and these temperature variations introduced disturbances into the images that frustrated the astronomers in their pursuit of the finest detail. Hale's response to this limitation demonstrated the progressive nature of his thinking about instrument design. If horizontal light paths near the ground introduced thermal disturbances, then the solution was to send the light vertically, through a tall tower that would lift the optical path above the most turbulent air. The 60-foot Solar Tower Telescope, completed in 1908, represented this new approach, its skeletal framework rising above the mountaintop and carrying at its summit a celostat that directed sunlight straight down through the tower to a spectrograph chamber below ground level. The underground placement of the spectrograph kept it at a stable temperature, free from the expansions and contractions that changes in warmth would cause, and the vertical light path proved far steadier than the horizontal one had been. This instrument allowed Hale to make one of the most significant discoveries in the history of astrophysics, for in 1908, while studying the spectrum of light from sunspots, those dark blemishes that appear and fade on the solar surface, he detected the unmistakable signature of a magnetic field. The phenomenon Hale observed was the Zeeman effect, named for the Dutch physicist Peter Zeeman, who had demonstrated in 1896 that spectral lines split into multiple components when the light source is immersed in a magnetic field. When Hale examined the spectrum of sunspot light through his tower telescope, he found precisely this splitting, the dark absorption lines that normally appeared single now showing themselves to be divided, and the pattern of this division indicated magnetic field strengths of remarkable intensity, thousands of times stronger than the magnetic field of Earth. This was the first detection of magnetism anywhere beyond our own planet, and it transformed our understanding of solar physics, revealing that sunspots were not merely cooler regions of the solar surface, but were instead the visible manifestations of intense magnetic activity, tubes of magnetic force rising from deep within the sun to pierce its glowing surface. Encouraged by the success of the 60-foot tower, Hale proceeded to plan an even larger instrument, and in 1912 the 150-foot solar tower telescope came into operation. This extraordinary structure dominated the Mount Wilson skyline, its tall framework painted white to minimize solar heating, and it carried the principles of the earlier tower to their logical extension, lifting the light-gathering mirrors still higher above the ground and directing the sunlight down to a spectrograph chamber that descended 75 feet below the surface. With this instrument, solar astronomers could study the finest details of the solar spectrum, measuring the wavelengths of light with exquisite precision and tracking the changes in sunspots and other solar phenomena over days and months and years. The tower telescopes of Mount Wilson established a tradition of systematic solar observation that would continue for decades, building up a record of solar activity that proved invaluable for understanding the cycles and rhythms of our star. While Hale pursued his solar research with the tower telescopes, he had not abandoned his ambitions for nighttime astronomy, and indeed the most famous instruments of Mount Wilson would be the great reflecting telescopes designed for observing stars and nebulae. The 60-inch reflector, which received its first light in 1908, the same year as Hale's sunspot magnetism discovery, was at that time the largest operational telescope in the world. Its primary mirror, a disc of glass 2.5 tons in weight that had been cast in France and polished with painstaking care at the Pasadena optical shop. The mirror collected light with an efficiency far beyond any previous instrument, and when turned toward the heavens it revealed stars too faint to have been seen before, resolved the fuzzy patches of distant star clusters into individual points of light, and showed the spiral structure of certain nebulae with a clarity that stirred even the most seasoned observers. The funding for the 60-inch reflector had come from the Carnegie Institution, and the relationship between Hale and Andrew Carnegie himself would prove one of the most fruitful partnerships in the history of science. Carnegie, the Scottish-American steel magnate who had devoted his later years to philanthropic giving on an enormous scale, took a personal interest in the Mount Wilson enterprise. He visited the observatory in 1910, making the journey up the mountain trail to see for himself what his institution's support had helped to create, and what he found there evidently impressed him deeply, for his contributions to Mount Wilson would eventually exceed $10 million, a sum almost difficult to comprehend in the currency of that era. Carnegie's support enabled not only the construction and operation of the telescopes, but also the development of the physical laboratories where instruments were designed and built, and the hiring of the skilled astronomers and technicians who would make the observatory productive. The practical arrangements for life and work on the mountain required considerable planning, for Mount Wilson was not a place where one could easily come and go. The Mount Wilson Hotel, completed in 1905, provided accommodation for astronomers, visiting scientists, and the occasional tourist who made the climb, though tourist access was carefully limited to avoid disruption of the scientific work. The hotel, a modest wooden structure with dormitory rooms and a common dining hall, became a place of intellectual community, where astronomers gathered after their nights at the telescope to discuss their observations and speculate about their meaning. The mule trains that carried equipment up the trail also brought food and supplies, and the rhythm of these supply expeditions became part of the routine of mountain life. The sound of bells on the lead mule announcing arrivals that broke the high silence of the summit. Among the astronomers who contributed most significantly to the Mount Wilson program was Walter Adams, who had come to work with Hale and who would eventually succeed him as director of the observatory. Adams devoted himself to the spectroscopic study of stars, analyzing the light from distant suns to determine their chemical composition and physical properties. His work on measuring stellar temperatures helped establish the methods by which astronomers could classify stars according to their spectral characteristics, arranging them into sequences that reflected their surface temperatures and stages of evolution. Adams showed that the spectrum of a star contained information not only about what elements were present in its atmosphere but also about how hot that atmosphere was. And this work contributed to the development of the Hertzsprung-Russell diagram, which became a fundamental tool for understanding the nature and life cycles of stars. Seth Nicholson came to Mount Wilson as a young graduate student and remained associated with the observatory for decades, contributing to the solar observing program with diligent and systematic work. Nicholson made daily observations of sunspots, recording their positions and appearances, tracking their changes over time, and helping to maintain the continuous record of solar activity that made Mount Wilson a world center for such research. But Nicholson is perhaps best remembered for discoveries he made during nighttime observations, for while studying the vicinity of Jupiter, he detected 4 previously unknown moons of that giant planet, small satellites too faint to have been noticed before but revealed by the light-gathering power of the Mount Wilson instruments. These discoveries, made between 1914 and 1951, added to the known family of Jupiter's attendant worlds and demonstrated that even careful observations of familiar objects could yield unexpected findings. Hale himself, despite his extraordinary achievements, struggled throughout his life with episodes of severe mental disturbance that periodically interrupted his work. He experienced what were described as nervous breakdowns, periods of debilitating exhaustion and psychological turmoil that required him to withdraw from his duties and seek rest and treatment. During some of these episodes, he reported experiencing hallucinations, including visitations from a small figure he described as an elf, a presence that seemed to offer him advice and with which he felt compelled to converse. These experiences troubled Hale deeply, and he consulted various physicians and specialists in search of relief, though the treatments available in that era offered limited help. It is a testament to his determination and to the support of his colleagues that he continued to make productive contributions to astronomy despite these afflictions, returning from each period of illness to resume his work and to plan ever more ambitious instruments. The years between 1904 and 1917 saw Mount Wilson transformed from a bare summit accessible only by mule trail into one of the world's preeminent astronomical research stations. The solar telescopes gathered data that reshaped our understanding of the Sun, revealing it as a body governed by powerful magnetic forces whose effects extended outward through the solar system. The 60-inch reflector proved that large reflecting telescopes could achieve the performance necessary for serious astronomical research, demonstrating the technology that would enable even larger instruments in the years to come. And the community of scientists who gathered on the mountain, working together through long nights and sharing their ideas and findings, established a model for observatory research that influenced institutions around the world. The mountain that had once known only the footsteps of hunters and the occasional hiker now hosted instruments that reached across light years of space, gathering the ancient light of distant stars and translating it into knowledge about the universe we inhabit. The story of the Hooker telescope begins, as so many great scientific instruments do, with a combination of ambition, patience, and the willingness of a wealthy benefactor to fund what must have seemed, at the time, an almost impossible undertaking. John D. Hooker was a Los Angeles hardware merchant who had accumulated considerable wealth, and he possessed that particular quality of mind that draws certain practical men toward the abstract mysteries of the universe, a fascination with the stars that could not be satisfied by merely gazing upward on clear California evenings. In 1906, Hooker made an initial contribution of $45,000 toward the construction of a telescope that would dwarf anything then in existence, a reflecting telescope with a primary mirror measuring 100 inches in diameter, which would gather light from objects so distant and so faint that no human eye had ever perceived them, and which would, though no one could have known it at the time, fundamentally alter our understanding of the cosmos and our place within it. George Eloy Hale, who had already overseen the construction of the 60-inch reflector on Mount Wilson, and who seemed constitutionally incapable of building anything other than the largest telescope in the world, immediately set about the task of creating this new instrument. The challenges were formidable in ways that are difficult to fully appreciate from our present vantage point, when large telescopes dot mountaintops across the globe and the techniques for their construction have been refined over more than a century of practice. In 1906, no one had ever cast a glass disc of such dimensions. No one had ever ground and polished a mirror of such size to the exacting tolerances required for astronomical work, and no one had ever built a mounting capable of tracking the stars with sufficient precision while supporting such enormous weight. Each of these problems would have to be solved in sequence, and each solution would require years of patient effort and the development of entirely new techniques. The mirror blank itself was ordered from the Saint-Gobain Glassworks in France, a company with centuries of experience in the manufacture of fine glass, though nothing in their long history had prepared them for the task of producing a single piece of glass weighing 4.5 tons and measuring over 8 feet across. The difficulties began almost immediately, as the sheer mass of molten glass required for such a casting behaved in ways that were difficult to predict and even more difficult to control. The first attempt at casting the blank took place in 1908. And when the glass had cooled sufficiently to be examined, the workers at Saint-Gobain discovered that it was riddled with bubbles, small pockets of trapped air that had failed to rise to the surface during the cooling process and that now formed imperfections distributed throughout the body of the disk. A second attempt was made, and a third, but each casting emerged from the annealing oven with similar flaws, and by the time a somewhat acceptable blank was finally produced, in late 1908, it still contained bubbles that caused considerable concern among those who would eventually have to work with it. John D. Hooker, who had expected his generosity to result in a functioning telescope within a reasonable span of time, grew increasingly impatient as the years passed and the instrument remained incomplete. He was a businessman accustomed to projects that proceeded according to schedule and budget, and the endless delays and unforeseen complications of the telescope project tested his patience severely. The flawed mirror blank was a particular source of frustration, and there were times when Hooker questioned whether his money had been well spent, whether the entire enterprise might not end in failure, with nothing to show for his investment but an oversized disk of defective glass gathering dust in some warehouse. Hale, who was himself prone to periods of severe nervous exhaustion brought on by the pressures of his work, had to manage not only the technical challenges of the project, but also the expectations of its principal benefactor. And this diplomatic task required a delicacy of touch that did not come naturally to a man whose mind was more at home among the abstractions of physics and astronomy than in the drawing rooms of wealthy patrons. The mirror blank arrived in Pasadena in December of 1908, having crossed the Atlantic Ocean by steamship and then traveled by rail from the port of New Orleans to California, a journey of thousands of miles during which the precious cargo had to be protected from shock and vibration that might have introduced additional stresses into the already compromised glass. The blank was placed in storage at the Mount Wilson Observatories optical shop, located not on the mountain itself but in the city below, where the work of grinding and polishing would be carried out over the following years. George Willis Ritchie, a skilled optician who had already demonstrated his abilities in the figuring of the 60-inch mirror, was given the task of transforming this rough disk of glass into a precision optical surface capable of bringing distant starlight to a perfect focus. It was work that could not be hurried, that required the patient removal of glass in quantities measured in millionths of an inch, and that demanded constant testing and retesting to ensure that the curve of the mirror matched the mathematical ideal with sufficient accuracy. Ritchie was a perfectionist of the most demanding sort, and his relationships with his colleagues were often strained by his unwillingness to compromise on matters of optical quality and his conviction that his own methods were superior to those of others. His conflicts with Hale grew more pronounced as the years passed, rooted in disagreements over telescope design, over the proper treatment of optical surfaces, and over questions of credit and recognition that seem petty in retrospect, but that loomed large in the minds of men whose work consumed their entire lives. Ritchie favored a different optical configuration than the one Hale had chosen for the 100-inch telescope, and he believed that his ideas were being dismissed without adequate consideration, a grievance that festered and eventually contributed to a complete rupture between the two men. But during the years of grinding and polishing the great mirror, these tensions remained largely beneath the surface, and the work proceeded with the slow deliberation that such precision demanded. The transport of the completed mirror from Pasadena to the summit of Mount Wilson presented challenges of a different sort, challenges that were more physical than intellectual but no less daunting for that. The road up the mountain was 9 miles long, narrow, winding, and steep, with grades that approached 23% in places and curves so sharp that the truck carrying the mirror sometimes had to make multiple attempts to negotiate them. The mirror, now polished to its final figure and more fragile than it had been as a rough blank, was crated and loaded onto a specially designed truck, and the journey began in the early morning hours to take advantage of cooler temperatures and reduced traffic. Progress was agonizingly slow, with the truck crawling upward at walking pace while workers went ahead to clear obstacles and check the road surface for hazards. One particularly difficult section of the road required 7 hours to traverse, 7 hours during which the driver coaxed the heavily laden vehicle around a series of switchbacks while the precious cargo shifted almost imperceptibly in its crate, and everyone involved held their breath and hoped that the road would hold and the truck would not slip backward over the edge. The mirror arrived safely at the summit, where the telescope mounting and dome had been under construction for years, and the work of installing the optical system in its mechanical framework began. The mounting itself was a marvel of precision engineering, designed to support the weight of the mirror and its cell, the secondary mirror, the observer's cage, and all the associated instrumentation, while allowing the entire assembly to rotate smoothly on two axes to track objects as the Earth turned beneath the stars. The problems that had been solved in building the 60-inch telescope now had to be solved again at larger scale, and new problems emerged that had not been anticipated. Problems related to flexure and thermal expansion and the behavior of materials under loads that had never before been applied to astronomical instruments. First light for the Hooker telescope came on the night of November 1st, 1917, and the initial observations seemed to confirm the worst fears of those who had worried about the bubbles in the mirror blank. When Hale and his colleagues pointed the great instrument at the bright star Vega, the image they saw in the eyepiece was not the crisp point of light they had hoped for, but a distorted, wavering blob that suggested something was seriously wrong with the optical system. The mirror appeared to be ruined, its surface deformed in ways that made it useless for serious astronomical work, and there were moments of genuine despair among the small group gathered at the telescope that night. But Hale, who had experienced setbacks before and who understood the behavior of large optical systems better than almost anyone else alive, suspected that the problem might not be permanent. The mirror had been exposed to the warmth of the day and had not yet reached equilibrium with the cooler night air, and this temperature difference was causing the glass to expand unevenly, distorting the carefully figured surface into a shape that bore little resemblance to the mathematical paraboloid that Ritchie had so painstakingly produced. The observers waited through the night, allowing the mirror to cool, and as the hours passed and the temperature of the glass slowly equalized, the image of Vega in the eyepiece gradually improved. By the early morning hours, the star had sharpened into a tiny disk surrounded by diffraction rings, the characteristic pattern produced by a well-figured mirror, and it became clear that the telescope was not ruined after all. The bubbles in the glass, which had caused so much concern during the years of grinding and polishing, turned out to have little effect on the optical performance of the mirror, and the Hooker telescope began its long career as the most powerful instrument for exploring the universe that humanity had ever possessed. In the years that followed, the 100-inch telescope transformed our understanding of the cosmos in ways that its builders could scarcely have imagined. Edwin Hubble, a young astronomer who had come to Mount Wilson after serving in the First World War, used the great instrument to study the faint spiral nebulae that had puzzled astronomers for generations. The question of whether these objects were relatively nearby clouds of gas within our own stellar system or distant assemblages of stars comparable to the Milky Way itself had been debated for decades, and the evidence available from smaller telescopes had been insufficient to settle the matter definitively. But the light-gathering power of the Hooker telescope, combined with the steady skies of Mount Wilson and the patient accumulation of photographic exposures over many nights, allowed Hubble to identify individual stars within the Andromeda Nebula, stars of a type whose intrinsic brightness was well understood and whose apparent faintness therefore indicated an enormous distance. In 1923 and 1924, Hubble presented evidence that Andromeda and the other spiral nebulae were not minor features of our own galaxy but independent stellar systems lying millions of light-years beyond its boundaries, and the universe suddenly became vastly larger than anyone had previously supposed. The 100-inch telescope also played a crucial role in the discovery of cosmic expansion, the observation that distant galaxies are receding from us at speeds proportional to their distances, an observation that implied the universe had a beginning in time and has been growing ever since. This work required not only the telescope itself, but also the skill and dedication of observers who could extract the maximum amount of information from the faint light of distant objects. And among the most remarkable of these observers was Milton Humason. Humason had come to Mount Wilson not as a trained astronomer but as a mule driver, hauling supplies up the steep mountain trails during the construction of the observatory, and he had stayed on as a janitor and general assistant before gradually working his way into more responsible positions. His formal education was limited, but his skill as an observer was extraordinary, and he possessed the patience and the steady hands required to guide a telescope for hours on end, while a photographic plate slowly accumulated the light of a galaxy so distant that it appeared as nothing more than a faint smudge even in the largest telescope on Earth. Humyson's collaboration with Hubble produced some of the most important observations in the history of astronomy, measurements of the redshifts and distances of galaxies that revealed the expansion of the universe and that laid the foundation for modern cosmology. The former mule driver and the former Rhodes Scholar made an unlikely pair, but their partnership was extraordinarily productive, and the data they gathered from the summit of Mount Wilson using the Hooker telescope shaped our understanding of the cosmos for generations to come. The Great Mirror, with its bubbles and its troubled history, had become a window onto the universe, and through that window humanity glimpsed for the first time the true scale and grandeur of creation. As the great telescopes of the late 19th century grew larger and more powerful, astronomers began to understand that the quality of their observations depended not only upon the precision of their instruments but also upon the steadiness of the air through which they gazed. The atmosphere, that thin blanket of gases surrounding our planet, proved to be both a blessing and a complication, for while it sustained the astronomers in their work, it also introduced distortions and tremors into the light arriving from distant stars. This realization led to a quiet but methodical quest that would span decades and continents, as patient observers sought out those rare locations where the air held itself still enough to permit the clearest possible views of the heavens above. The phenomenon that astronomers came to call seeing refers to the steadiness of stellar images as viewed through a telescope, and it differs from the more familiar twinkling that one notices with the unaided eye on a clear evening. When air of different temperatures mixes and swirls above an observatory, the paths of light rays bend and shift in unpredictable ways, causing star images to dance and blur and spread themselves across larger portions of the field of view than they would otherwise occupy. On nights of poor seeing, even the finest telescope renders stars as fuzzy, bloated disks rather than the sharp points of light that theory predicts, and delicate details on planetary surfaces become smeared beyond recognition. The search for locations blessed with superior seeing would become one of the defining endeavors of astronomical site selection during this period. William Henry Pickering, brother of the more widely known Edward Charles Pickering, who directed Harvard College Observatory, devoted much of his career to this systematic investigation of atmospheric conditions at potential observatory sites around the world. Beginning in the 1890s and continuing into the early 20th century, the younger Pickering organized a series of expeditions that carried small telescopes and measuring instruments to locations as varied as Jamaica in the Caribbean, the mountains of Southern California, the high plateaus of Peru, and the elevated regions of South Africa. At each site, he and his assistants would establish temporary observing stations and spend weeks or months recording the behavior of star images under varying conditions of weather and season. The methods Pickering employed were straightforward yet required considerable patience and consistency in their application. Observers would select a star of moderate brightness positioned at a convenient elevation above the horizon, and then they would examine its image through the telescope at high magnification, noting the diameter to which the stellar disk appeared to spread and the degree to which its edges wavered and shifted. On the calmest nights, a star might present itself as a compact, well-defined point surrounded by delicate diffraction rings, those circular patterns predicted by the wave theory of light. On poorer nights, the rings would dissolve into a general haze, and the central disk would swell and pulse as though breathing with the turbulent atmosphere above. Pickering also paid careful attention to scintillation, the rapid fluctuations in a star's brightness that occur as pockets of air with varying density pass across the line of sight. By timing these fluctuations and recording their amplitude, observers could gather additional information about the nature of atmospheric disturbance at different altitudes. Slow, gentle variations often indicated turbulence high in the atmosphere, while rapid, violent flickering suggested that the disturbed air lay closer to the ground, perhaps immediately above or around the telescope itself. Through the accumulation of many such observations across multiple sites, Pickering hoped to identify patterns that would guide the placement of future observatories. Concurrent with Pickering's wide-ranging surveys, a younger astronomer named Andrew Ellicott Douglas was conducting site testing work that would lead to one of the most famous observatory locations in America. In 1894, Douglas was dispatched by the wealthy amateur astronomer Percival Lowell to find a suitable location for a new observatory dedicated primarily to the study of Mars. Lowell believed that the red planet harbored evidence of intelligent life in the form of an extensive canal system, and he required a site where atmospheric conditions would permit the detailed observation of these putative features. Douglas traveled through the American Southwest, carrying a borrowed telescope and camping in locations that seemed promising based upon their elevation, remoteness, and general aridity. He tested sites in Arizona Territory, including Tucson, Tombstone, Tempe, and a small community called Flagstaff situated on the Colorado Plateau at an elevation of roughly 7,000 feet above sea level. At each location, Douglas would observe for several nights, recording the steadiness of star images and the overall transparency of the sky. The Flagstaff site, perched on a mesa west of the town, ultimately received his recommendation, and their Lowell Observatory was established and continues its work to this day. The techniques for quantifying seeing grew more sophisticated as the decades passed. The German physicist Johannes Franz Hartmann developed a test that bears his name, in which a mask with two apertures is placed over the objective of a telescope, and the observer examines how the two beams of light combine at focus. When the atmosphere is perfectly steady, the two beams merge into a single sharp image, but when turbulence is present, they dance about one another in patterns that reveal the character of the disturbance. By analyzing these patterns, astronomers could separate the effects of ground-level heating from those of upper atmospheric turbulence, and they could make more informed judgments about whether a particular site suffered from correctable local conditions or from more fundamental atmospheric limitations. John A. Miller, working on behalf of the University of Arizona in the 1910s and 20s, conducted site surveys throughout the territory that would inform the eventual establishment of Stewart Observatory. Miller investigated numerous peaks and elevated locations in southern Arizona, hauling small telescopes up mountain trails and spending nights in camps that offered little in the way of comfort or amenity. His records, maintained with careful attention to date, time, temperature, and wind conditions, contributed to the growing body of knowledge about how terrain and local geography influenced the steadiness of the air above. A crucial insight that emerged from these decades of site testing was the importance of laminar airflow, which refers to the smooth, layered movement of air across a landscape without the swirling eddies that characterize turbulent flow. Astronomers discovered that the best seeing conditions often occurred at sites where steady winds passed over smooth, uniform terrain before reaching the observatory, allowing the air to settle into orderly layers that introduced minimal distortion into starlight. Conversely, locations where air passed over rough or thermally active surfaces tended to suffer from persistent turbulence that degraded observations regardless of other favorable factors. This principle helps to explain why the seeing at Mount Wilson, which had been excellent during the observatory's early years, gradually deteriorated as the city of Los Angeles expanded in the valleys below during the 1920s and 30s. The vast sprawl of buildings, roads, and paved surfaces generated tremendous amounts of heat during the day, and as this warm air rose and mixed with cooler air flowing in from the Pacific Ocean, it created turbulent plumes that drifted upward toward the mountain summit. The dome of disturbed air above the growing metropolis came to be known informally as the Los Angeles Seeing Dome, and it served as a cautionary example of how human development could compromise even the finest observatory sites over time. When astronomers at the Carnegie Institution began planning for a telescope far larger than any yet constructed, they recognized that site selection would be even more critical than it had been for previous instruments. A telescope with a 200-inch mirror would be so sensitive to atmospheric effects that only the steadiest sites could permit it to achieve its full potential. Walter Sidney Adams, who had succeeded George Ellery Hale as director of Mount Wilson Observatory, organized a comprehensive site testing campaign during the 1930s that would evaluate numerous candidate locations across Southern California and beyond. Adams equipped his teams with portable telescopes of modest aperture, instruments small enough to be transported by mule or truck to remote mountain locations yet large enough to provide meaningful measurements of seeing conditions. At each site, observers would establish a camp and remain for weeks at a time, conducting nightly observations whenever weather permitted and maintaining detailed logs of atmospheric steadiness, sky transparency, wind speed and direction, temperature, and humidity. The observers worked through all seasons, recognizing that a site which performed well during summer might prove disappointing during winter storms, or vice versa. The testing campaign eventually focused attention on Palomar Mountain, located some 100 miles southeast of Mount Wilson in the Peninsula Ranges of San Diego County. The site offered several advantages that the accumulated data confirmed. It lay far enough from Los Angeles that urban heating effects were minimal. It rose to sufficient elevation that observers worked above the marine layer of moist air that often blanketed the coastal plain, and the terrain to the west consisted of relatively smooth, gradual slopes that promoted laminar airflow. After years of testing and comparison, Palomar was selected, and construction of the Great Dome began. A lesser-known aspect of site testing during this era involved the use of data gathered by weather services and military organizations for purposes entirely unrelated to astronomy. Meteorologists had been launching balloons carrying instruments aloft since the late 19th century, and these balloon soundings provided vertical profiles of temperature, humidity, and wind speed through the atmosphere. Astronomers recognized that this information could help them understand where turbulent layers were likely to form and at what altitudes the most troublesome disturbances occurred. Military aviation, which expanded dramatically during and after the First World War, also contributed data about upper atmospheric conditions that proved useful in evaluating potential observatory sites. Throughout all of this systematic testing, the human element remained essential. The instruments and techniques could quantify aspects of atmospheric behavior, but ultimately the work depended upon individual astronomers willing to spend months in primitive conditions, night after night, recording observations with patience and consistency. These observers lived in tents or small cabins, often in locations accessible only by difficult trails, and they endured extremes of temperature and the loneliness of isolation while performing their methodical work. Edison Pettit, who would later become known for his solar observations at Mount Wilson, exemplified the dedication required for site testing work during his younger years. Pettit maintained meticulous seeing logs that recorded conditions hour by hour throughout long nights of observation, noting not only the apparent diameter of star images but also the character of their motion, whether they wandered slowly and gently or danced in rapid, irregular patterns. His logs, filled with careful numerical estimates and descriptive notes, represent the kind of painstaking documentation that accumulated across many observers and many sites to form the empirical foundation of site selection science. The camps where these observers worked often lacked running water, electricity, and reliable shelter from wind and cold. Food supplies had to be packed in periodically, and communication with the outside world might be limited to occasional visits from resupply parties or the rare trip down the mountain for provisions and rest. Under such conditions, maintaining the discipline to observe every clear night and to record data with consistent precision required a particular temperament, one that found satisfaction in the slow accumulation of knowledge and the service of a larger scientific purpose. By the middle of the 20th century, the quest for perfect seeing had established principles and methods that would guide observatory site selection for generations to come. The work of Pickering and Douglas and Miller and Adams and Pettit and countless others had demonstrated that finding the best locations for telescopes required not only theoretical understanding of atmospheric physics, but also the willingness to test and measure and compare across many sites and many seasons. The mountains that emerged from this process as premier observatory locations, places like Palomar and Kitt Peak and sites yet to be developed in later decades, owed their selection to those patient observers who had spent their nights watching stars and recording what they saw, gradually building the empirical foundation upon which great telescopes could stand with confidence that the air above would hold steady enough to let them see. In the high desert of northern Arizona, where the ponderosa pines grow tall and the air settles into a stillness that seems to hold the very stars in place, there stands an observatory that was born from one man's singular vision, and perhaps, one might say, from his singular obsession as well. The story of Lowell Observatory is, in many respects, the story of Percival Lowell himself, a wealthy Bostonian who turned his considerable fortune and his restless intellect toward the red planet Mars, and who built upon a mountain a temple to his convictions about life on other worlds. That his convictions would prove incorrect does not diminish the importance of what was accomplished on that Arizona hilltop, for science often advances through passionate error just as surely as it does through careful confirmation, and the instruments that Lowell assembled for his Martian studies would go on to reveal truths about the universe that he himself never anticipated. Truths that would reshape our understanding of the cosmos in ways far more profound than any canal on a dying world. Percival Lowell came to astronomy relatively late in life, having spent his earlier years in business and diplomacy, including nearly a decade in Japan and Korea, where he developed a keen appreciation for Eastern philosophy and wrote several well-regarded books on Asian culture. He was born in 1855 into one of Boston's most distinguished families, the Lowells of Harvard and textile mills fame, and his brother Abbott Lawrence Lowell would later serve as president of Harvard University. Percival himself attended Harvard and graduated with distinction in mathematics, but the conventional paths of commerce and academia did not entirely satisfy his restless nature. And when he encountered the writings of the Italian astronomer Giovanni Schiaparelli regarding the so-called canali of Mars, something stirred within him that would come to define the remainder of his days. Schiaparelli had observed and mapped linear features on the Martian surface during the favorable opposition of 1877, and though the Italian word canali simply means channels, with no implication of artificial construction, the term was translated into English as canals, carrying with it the suggestion of engineering, of purpose, of minds at work upon another world. The year 1894 presented an opportunity that Lowell was not willing to let pass, for Mars would come into opposition that summer, meaning the Earth and Mars would align on the same side of the Sun, bringing the two planets into relatively close proximity and affording observers the best possible views of the Martian surface. Lowell understood that if he wished to study Mars under optimal conditions, he would need an observatory purpose-built for planetary observation, situated at a location where the atmosphere was steady and clear, where the seeing, as astronomers call it, would allow the finest details to be discerned through the telescope's eyepiece. He did not have years to deliberate, for the opposition would not wait, and so he embarked upon a remarkably rapid campaign of site selection and construction that demonstrated both his determination and his substantial financial resources. To assist in choosing a location, Lowell drew upon data and recommendations from William Henry Pickering, the younger brother of Edward Charles Pickering, who directed the Harvard College Observatory. William Pickering had experience with astronomical site testing and had recently returned from observations conducted in Peru at Harvard's southern station at Arequipa. The requirements were specific and demanding, for planetary observation differs from deep sky work in its need for atmospheric stability rather than merely atmospheric transparency, and Lowell sought a place where the air would lie still and untroubled, where thermal currents would not blur the delicate markings he hoped to discern upon the face of Mars. Arizona Territory, with its high elevation, dry climate, and clear skies, emerged as a promising candidate, and Pickering was dispatched to test various sites throughout the region. The town of Flagstaff, situated upon the Colorado Plateau at an elevation of approximately 7,000 feet, with the peak that would bear the observatory rising to some 7,250 feet above the level of the sea, proved to possess the qualities Lowell sought. The thin mountain air, the distance from large bodies of water that might otherwise generate atmospheric disturbance, the relative isolation from the lights and smoke of industry, all these factors combined to make it a suitable home for the serious study of the planets. Lowell purchased the land, which the locals would come to call Mars Hill, and set about constructing an observatory with remarkable speed, for the opposition was approaching and there was no time for leisurely deliberation. The initial observations during that first opposition of 1894 were conducted with borrowed equipment, but Lowell soon commissioned a telescope worthy of his ambitions, a magnificent 24-inch refracting telescope from the renowned firm of Alvan Clark & Sons. The Clark firm had by this time established an unparalleled reputation for the construction of large refractors, having built the great lenses for the Lick Observatory and many other institutions, and the instrument they delivered to Flagstaff was a superb example of the optical maker's art. A refractor of 24 inches aperture gathers light efficiently and, when properly figured, produces images of exceptional sharpness, qualities that are particularly valuable for the study of planetary surfaces where fine detail is paramount. The telescope was housed in a dome of traditional design, and there, night after night when Mars rode high in the Arizona sky, Percival Lowell pressed his eye to the eyepiece and drew what he believed he saw upon the rusty face of that neighboring world. What Lowell saw, or believed he saw, was an intricate network of linear features crisscrossing the Martian surface, straight lines, and geometric patterns that seemed to him utterly inconsistent with any natural process. He mapped these features with painstaking care, recording their positions and intersections, noting where they converged at darker spots he termed oases. From these observations he constructed a theory that was as elaborate as it was, ultimately, unfounded, a theory of a dying civilization struggling to survive upon a world where water had grown desperately scarce. The canals, in Lowell's interpretation, were vast engineering works constructed by intelligent Martians to transport water from the polar ice caps to the parched equatorial regions, a planetary irrigation system of almost inconceivable scale, a testament to the ingenuity and desperation of a species fighting against the slow death of their world. He presented these ideas to the public with considerable literary skill, for Lowell was a gifted writer as well as an enthusiastic observer, and his books found a wide and receptive audience. Mars, published in 1895, laid out his observations and interpretations in accessible prose, painting a vivid picture of an ancient world where intelligent beings labored against the inevitable decline of their environment. Mars and Its Canals, which appeared in 1906, expanded upon these themes with additional observations and arguments, and Mars as the Abode of Life, published in 1908, continued to develop his case for Martian intelligence. The public was enchanted, for the notion of life on other worlds has always held a powerful appeal to the human imagination, and Lowell's Martians, with their noble struggle against planetary death, captured something of the anxieties and aspirations of the early 20th century. The scientific establishment, however, was considerably less convinced, and many professional astronomers regarded Lowell's canal observations with skepticism ranging from polite doubt to open dismissal. Among the most significant critics was Edward Emerson Barnard, the sharp-eyed observer at Lick Observatory who had discovered Amalthea, the fifth moon of Jupiter, and who possessed perhaps the finest visual acuity of any astronomer of his generation. Barnard studied Mars through the great 36-inch refractor at Mount Hamilton, an instrument with half again the aperture of Lowell's Clark telescope, and he simply could not see the canals that Lowell described in such confident detail. Where Lowell saw straight lines and geometric precision, Barnard saw only the irregular markings one might expect from natural geological and atmospheric processes. Other observers reported similar difficulties, finding that the canals seemed to vanish when viewing conditions were at their very best, suggesting that they might be optical illusions, artifacts of the human visual system straining to make sense of features at the very limit of perception. The debate over Martian canals would continue for decades, but time and improved instrumentation would ultimately vindicate the skeptics, for the canals were indeed illusory, products of the eye's tendency to connect disparate points into continuous lines when viewing is difficult and the features are barely perceptible. This was not fraud or deliberate deception on Lowell's part, for he unquestionably believed in what he saw, but rather an example of how the eager observer may find what he expects to find, how the mind may impose patterns upon randomness when it is sufficiently motivated to do so. It is a cautionary tale that science is absorbed into its collective wisdom, a reminder of the importance of independent confirmation and the dangers of passionate conviction unchecked by rigorous skepticism. Yet the story of Lowell Observatory does not end with the illusory canals, for the instruments and facilities that Lowell established continued to produce astronomical observations of genuine and lasting importance long after the Martian controversy had faded into historical curiosity. Among the astronomers who worked at Flagstaff was Vesto Melvin Slipher, a quiet and methodical observer from Indiana who joined the observatory staff in 1901 and who would go on to make discoveries of profound cosmological significance using the very same spectrograph that had been intended primarily for planetary work. Between 1912 and 1914, Slipher undertook a systematic program of measuring the spectra of spiral nebulae, those curious pinwheel-shaped objects whose true nature was still hotly debated, with some astronomers believing them to be nearby gas clouds within our own Milky Way and others suspecting they might be distant island universes in their own right. Slipher's spectrographic work revealed something remarkable. for he found that the spectral lines of these nebulae were shifted from their expected positions, with most showing a shift toward the red end of the spectrum. This redshift, interpreted through the Doppler effect, indicated that the spiral nebulae were moving away from us at considerable velocities, velocities far greater than anything observed among the stars of our own galaxy. The significance of Slipher's measurements would not be fully appreciated until the following decade, when Edwin Hubble at Mount Wilson established definitively that the spiral nebulae were indeed external galaxies, and when Hubble combined Slipher's velocity measurements with his own distance determinations to reveal the expansion of the universe itself. The redshift distance relation that Hubble announced in 1929, one of the most important discoveries in the history of astronomy, rested in substantial part upon the careful spectrographic work that Vesto Slipher had performed at Lowell Observatory in the years before the First World War. It is one of the pleasant ironies of scientific history that an observatory founded to study an imaginary Martian civilization contributed fundamentally to our understanding of the structure and evolution of the cosmos. Percival Lowell himself did not live to see these cosmological developments, nor did he live to see the culmination of another project that had occupied much of his later years, the search for a trans-Neptunian planet that he termed Planet X. Lowell had become convinced through mathematical analysis that the orbits of Uranus and Neptune showed perturbations that could only be explained by the gravitational influence of an unknown body lurking in the outer reaches of the solar system. And beginning in 1906, he devoted considerable resources to the photographic search for this hypothetical world. The work was tedious and painstaking, requiring the comparison of photographic plates taken on different nights to detect the slow motion of a planetary body against the fixed background of stars. And despite years of effort, the search was unsuccessful during Lowell's lifetime. Percival Lowell died in 1916, and the search for Planet X was subsequently delayed for more than a decade by legal disputes over his estate, disputes in which his widow Constance played a central and contentious role. Constance Lowell contested the provisions of her husband's will, particularly those relating to the observatory and its endowment, and the resulting litigation consumed years and substantial resources that might otherwise have supported continued research. It was not until these difficulties were resolved and new equipment was acquired that the search could resume in earnest. In 1929, a young Kansas farm boy named Clyde William Tambour was hired to conduct the systematic photographic survey that the Planet X search required. Tambour was largely self-taught in astronomy, having built his own telescopes and made careful drawings of the planets that impressed the observatory staff, and he brought to the task a patience and meticulousness that would prove essential. Using a new 13-inch astrograph and a blink comparator that allowed rapid switching between photographic plates to reveal any object that had moved, Tambour laboriously examined the sky, night after night, plate after plate. On February 18, 1930, Tambour found what he was looking for, a faint point of light that had shifted position between plates taken on January 23 and January 29. Further observations confirmed the discovery, and on March 13, 1930, the anniversary of both Percival Lowell's birth and William Herschel's discovery of Uranus, the existence of a new planet was announced to the world. The planet was eventually named Pluto, at the suggestion of an 11-year-old English schoolgirl, and its astronomical symbol incorporated the letters P and L, honoring the initials of Percival Lowell, whose vision and persistence had initiated the search. It would later become apparent that Pluto was far too small to have produced the orbital perturbations that Lowell had calculated, and indeed, refined measurements would eventually show that those perturbations had been largely illusory, the result of slight errors in the observational data. The discovery of Pluto, in other words, was something of a fortunate accident, a case of finding the right answer through incorrect reasoning. But find it they did, and the little world at the edge of the solar system stands as a lasting monument to the Mountain Observatory and to the man who built it. A man who was wrong about Mars, but whose wrongness nonetheless advanced the cause of human knowledge in ways that mere correctness might not have done. In the early morning hours, when the astronomers descended from their telescope domes after long nights of observation, their work was only half complete. The photographic plates they carried, those precious glass rectangles bearing the faint impressions of starlight, required careful and methodical analysis before they could yield any scientific meaning. This painstaking work of measurement and classification fell largely to a group of women whose contributions would prove essential to our understanding of the cosmos, though their names appeared far less frequently in the published literature than those of the men who had aimed the telescopes at the sky. The story of women in mountaintop astronomy during this period is one of remarkable intellectual achievement accomplished within deeply constraining circumstances, and it begins most properly at the Harvard College Observatory, where a pioneering program of stellar classification would eventually reshape our understanding of what stars truly are. Edward Charles Pickering, who served as director of the observatory from 1877 until 1919, found himself in need of dedicated assistants to process the thousands of photographic plates accumulating in his archives. The traditional hiring pool of male assistants proved expensive and, in Pickering's estimation, sometimes insufficiently diligent for the repetitive precision work required. He turned instead to women, whom he could employ at significantly lower wages, typically between 25 and 50 cents per hour, a fraction of what male assistants might expect for comparable labor. The women who worked in what became known informally as the Harvard computers represented some of the finest analytical minds of their generation, though their official positions rarely reflected their true capabilities. They worked in a crowded room examining photographic plates through magnifying glasses, recording their observations in careful handwriting, performing the mathematical calculations that transformed raw data into usable astronomical knowledge. The work demanded exceptional patience, keen eyesight, and an ability to maintain concentration through hours of repetitive measurement, and the women who excelled at it often possessed scientific intuitions that far exceeded the mechanical requirements of their assigned tasks. Williamina Patton Stevens Fleming came to the observatory by an unusual path, having initially worked as a maid in Edward Pickering's household after emigrating from Scotland. Her evident intelligence impressed Pickering, who hired her in 1881 to perform clerical duties, but she quickly demonstrated abilities that led to her involvement in the observatory spectroscopic work. Fleming developed a classification system for stellar spectra based on the relative strength of hydrogen absorption lines, organizing stars into categories designated by the letters A through O. This system, while later refined by her colleagues, represented the first comprehensive attempt to sort the stellar population by spectroscopic characteristics rather than mere brightness or position. Fleming's contributions extended well beyond classification work, as she discovered numerous astronomical phenomena during her examination of photographic plates, including the Horsehead Nebula in 1888 and dozens of novae and variable stars. She was eventually appointed curator of astronomical photographs in 1899, a title that acknowledged her expertise while still maintaining the hierarchical distinction between the women computers and the male astronomers who directed the observatory's research programs. Her published work appeared under her own name in some instances, though credit was not always consistently assigned during this era when the boundaries between discovery and assistance remained deliberately unclear. Annie Jump Cannon joined the Harvard computers in 1896, bringing with her a degree from Wellesley College and additional graduate study in physics and astronomy. She would spend more than 4 decades at the observatory, eventually becoming one of the most accomplished classifiers of stellar spectra in the history of astronomy. Cannon possessed an exceptional ability to examine a stellar spectrum and determine its classification almost instantaneously, a skill that seemed to her colleagues nearly intuitive in its speed and accuracy. She refined the earlier classification schemes into what became known as the Harvard spectral classification, organizing stars by temperature into the familiar sequence O, B, A, F, G, K, M, a system that remains in use today with only minor modifications. The scope of Cannon's classification work defies easy comprehension. Over the course of her career, she personally classified the spectra of approximately 350,000 stars for the Henry Draper catalog and its extensions, an undertaking that required examining each stellar spectrum on photographic plates and assigning it to the appropriate spectral class based on the pattern of absorption lines visible in the image. This monumental effort, published in multiple volumes between 1918 and 1924, with supplementary catalogues continuing afterward, provided the astronomical community with a standardized reference that enabled countless subsequent investigations into stellar physics and galactic structure. Cannon's expertise was universally acknowledged within the astronomical profession, and she received numerous honors, including an honorary doctorate from Oxford University in 1925, the first woman to be so recognized by that institution. Yet she remained formally classified as a technical assistant at Harvard until 1938, when she was finally appointed William Cranch Bond Astronomer, just 2 years before her retirement. The discrepancy between her actual contributions and her official position illustrated a pattern that repeated itself throughout this era, as institutions found ways to benefit from women's intellectual labor while declining to grant them the titles and salaries that their work merited. Henrietta Swan Leavitt joined the Harvard Computers in 1893 and specialized in the study of variable stars, those celestial objects whose brightness changes over time in periodic or irregular fashion. Her particular focus was on a class of variables known as Cepheids, named after the prototype star Delta Cephei, which exhibit regular pulsations in their luminosity with periods ranging from days to months. Leavitt examined photographic plates of the Magellanic Clouds, those companion galaxies visible from the southern hemisphere, identifying hundreds of variable stars and carefully measuring their periods and apparent brightnesses. In 1912, Leavitt published a discovery that would prove to be one of the most consequential findings in the history of astronomy. She observed that among the Cepheid variables in the small Magellanic Cloud, there existed a clear relationship between the period of a star's brightness variation and its intrinsic luminosity. Stars with longer periods were genuinely more luminous than those with shorter periods, and this relationship was consistent and predictable. Because all the stars in the Magellanic Cloud were at approximately the same distance from Earth, their apparent brightnesses provided a direct measure of their relative luminosities, allowing Leavitt to establish this period luminosity relationship with confidence. The implications of Leavitt's discovery extended far beyond the Magellanic Clouds themselves. If the period luminosity relationship could be calibrated using Cepheids at known distances, then any Cepheid variable anywhere in the universe could serve as a standard candle, its intrinsic brightness determinable from its period of variation. By comparing this intrinsic brightness to the star's apparent brightness as observed from Earth, astronomers could calculate the distance to that star and, by extension, to whatever stellar system contained it. This method would eventually enable Edwin Hubble and others to measure distances to galaxies beyond our own, fundamentally transforming our understanding of the scale of the cosmos. Leavitt's work exemplified both the possibilities and the limitations facing women in astronomy during this period. Her discovery ranks among the most important in the field. Yet she received no major awards during her lifetime and died of cancer in 1921 at the age of 53, before the full implications of her work had become apparent. She had no opportunity to extend her research into the distance measurements her discovery made possible, as her position at Harvard did not grant her access to the telescopes that would have been required for such observations. The work of building upon her foundational insight was left to others, predominantly men who had access to the larger instruments and the professional standing to pursue independent research programs. The constraints under which these women worked deserve careful attention, as they shaped both the nature of their contributions and the historical memory of their achievements. Women at major observatories were typically barred from using the large telescopes at night, either by explicit policy or by the practical difficulties of maintaining propriety in the remote mountaintop settings where these instruments were located. The night observing work was reserved for male astronomers, while women were assigned to daytime computing and analysis tasks that, however essential, were classified as support work rather than original research. This division of labor created a peculiar situation in which women performed much of the intellectual work that made astronomical discoveries possible, while being denied the opportunity to make those discoveries themselves. The men who exposed the photographic plates often received credit for the findings that emerged when those plates were analyzed by women computers working under their direction. The hierarchical structure of the observatory ensured that credit flowed upward to the directors and senior astronomers, while the women who actually performed the measurements and recognized the patterns were acknowledged, if at all, in footnotes or acknowledgement sections. Margaret Harwood represented a partial exception to these patterns, though her career also illustrated the limited pathways available to women who sought positions of genuine authority. After studying at Radcliffe College and completing graduate work at the University of California, Harwood became director of the Maria Mitchell Observatory on Nantucket Island in 1916, a position she would hold for 41 years until her retirement in 1957. The Maria Mitchell Observatory, founded in honor of America's first professional woman astronomer, was specifically dedicated to providing opportunities for women in the field, and Harwood used her position to advance both scientific research and the careers of her female students and assistants. Harwood's directorship was exceptional precisely because such positions were so rarely available to women at larger and better-funded institutions. The Maria Mitchell Observatory operated on a modest budget with limited equipment, and while Harwood conducted valuable research on variable stars and asteroid observations, she lacked access to the major telescopes that would have enabled more ambitious programs. Her long tenure demonstrated that women could lead scientific institutions effectively, a point that should hardly have required demonstration, but that nonetheless carried significance in an era when such examples remained rare. Charlotte Emma more sittily pursued her career through a different path, working primarily in solar spectroscopy rather than stellar observation. After completing her doctorate at the University of California in 1931, she collaborated extensively with Henry Norris Russell at Princeton University on the analysis of atomic spectra and their applications to astrophysics. Her work focused on identifying and cataloging the spectral lines produced by various elements in the solar atmosphere, a project that required mastery of both observational techniques and the emerging quantum theory that explained the origins of these spectral features. More Siddeley's contributions to atomic spectroscopy proved invaluable to generations of subsequent researchers. Her compilations of atomic energy levels and spectral line identifications, published through the National Bureau of Standards where she worked from 1945 onward, became standard references in both physics and astronomy. The painstaking nature of this work, requiring the correlation of vast amounts of spectroscopic data with theoretical predictions, exemplified the type of contribution that women in this era were often permitted to make, essential reference work that supported the more glamorous discoveries of others while receiving less public recognition. Cecilia Payne arrived at Harvard from Cambridge University in 1923 and produced what has been called the most brilliant doctoral thesis ever written in astronomy. Her 1925 dissertation demonstrated through spectroscopic analysis that stars are composed primarily of hydrogen and helium, with heavier elements representing only a tiny fraction of their mass. This finding contradicted the prevailing assumption that stellar compositions roughly matched the elemental abundances found on Earth, and it encountered initial skepticism from established figures in the field. Henry Norris Russell, one of the most influential astronomers of the era, initially doubted Payne's conclusions and advised her to soften her claims about hydrogen abundance in the published version of her thesis. She followed his advice, describing her results as spurious in light of the conventional wisdom, a decision she would later regret. Within a few years, Russell himself confirmed the essential correctness of Payne's analysis through independent methods and published findings that acknowledged her priority, though his paper on the subject received more attention at the time than her original work had garnered. Payne Gaposchkin, as she became known after her marriage to the astronomer Sergei Gaposchkin in 1934, remained at Harvard for the rest of her career, eventually becoming the first woman to achieve the rank of full professor in the Faculty of Arts and Sciences and the first woman to chair a department at Harvard. These milestones came late in her career, in 1956, more than 3 decades after her groundbreaking thesis had demonstrated abilities that should have been rewarded far sooner. Her trajectory illustrated both the eventual, if glacially slow, opening of opportunities for women in astronomy and the decades of diminished recognition and compensation that women endured even when their abilities matched or exceeded those of their male colleagues. In the quiet workshops and optical laboratories of the late 19th century, a gentle revolution was taking place, one measured not in dramatic discoveries but in the patient grinding of glass, the careful deposition of silver, and the slow refinement of techniques that would, over decades, transform our understanding of the universe. The instruments of astronomy, those elegant assemblages of glass and metal that perched atop mountains and peered into the darkness, were evolving with each passing year, becoming more sensitive, more precise, and more capable of capturing light that had traveled unimaginable distances to reach us. This is the story of that quiet evolution, of the craftsmen and scientists who devoted their lives to the seemingly simple task of gathering starlight and bending it to human purposes. And it is a story best told slowly, with attention to the small details that made all the difference. The astronomers of the 19th century faced a fundamental choice when designing their telescopes, a choice between 2 different ways of collecting and focusing light. The refractor telescope, which used a lens at the front end to bend incoming light rays toward a focus, had been the dominant instrument since the time of Galileo, and it possessed certain undeniable virtues. A well-made lens, properly supported in its cell, maintained its shape with admirable consistency, and the tube of a refractor was sealed against dust and the gentle deterioration that comes with exposure to the elements. But the refractor carried within its design a persistent difficulty, one that grew more troublesome as telescope makers attempted to build larger and larger instruments. This difficulty was chromatic aberration, the tendency of a simple lens to focus different colors of light at slightly different distances, producing images fringed with unwanted rainbow halos. Blue light, being bent more sharply than red, came to a focus closer to the lens, and so a star that should have appeared as a crisp point of light instead showed itself surrounded by colored rings, particularly troublesome when one wished to photograph the heavens or measure the precise positions of celestial objects. The optical makers of the 18th century had discovered that chromatic aberration could be reduced, though never entirely eliminated, by combining two lenses made of different types of glass, one of crown glass and one of flint glass, whose dispersive properties partially cancelled each other out. These achromatic doublets, as they were called, made large refractors practical, and the great visual refractors of the 19th century, culminating in the 40-inch instrument at Yerkes Observatory, represented the pinnacle of this technology. Yet the difficulty of obtaining large discs of optically pure flint glass, free from bubbles and striations, placed a practical limit on how large a refractor could be built, and the residual color still present in even the finest achromatic lenses meant that the reflecting telescope, which used a curved mirror instead of a lens and thus suffered no chromatic aberration whatsoever, remained an attractive alternative for those willing to contend with its own particular challenges. The early reflecting telescopes had employed mirrors made of specular metal, an alloy of copper and tin that could be polished to a lustrous surface but which tarnished with distressing rapidity when exposed to the atmosphere. A specular mirror might show a beautiful figure when freshly polished, but within months or even weeks, depending on the local conditions, its surface would grow dull and its reflectivity would diminish, requiring the astronomer to remove the mirror and send it away for repolishing, a process that not only interrupted observations but risked altering the carefully figured surface. The alloy was also heavy and prone to flexing under its own weight, making large specular mirrors difficult to support without introducing distortions. For these reasons, despite the theoretical advantages of reflectors, the great observatories of the mid-19th century generally preferred refractors, accepting their chromatic limitations in exchange for the stability and reliability that a glass lens could provide. The transformation of the reflecting telescope from a temperamental instrument into a reliable workhorse began in 1857, when the French physicist Léon Foucault demonstrated a new method for making telescope mirrors. Rather than casting a mirror from metal, Foucault took a disc of ordinary glass, ground, and polished it to the required curved shape, and then deposited a thin layer of silver onto its surface through a chemical process. The glass provided a stable foundation that held its shape far better than specular metal, while the silver coating, though it would eventually tarnish, could be removed and renewed without disturbing the underlying figured surface. This silver-on-glass technique, refined over the following decades, gradually shifted the balance of advantage toward the reflector. When a silver coating grew dull, the astronomer needed only to strip away the old silver and apply fresh silver through a relatively straightforward chemical bath, restoring the mirror to its original reflectivity without the risk of altering its carefully figured curve. The mirrors could also be made thinner and lighter than their speculum predecessors, since the glass was merely a substrate and need not possess the rigidity required of a solid metal mirror. The craft of making fine astronomical optics required not only theoretical knowledge but also a delicate touch, an almost intuitive understanding of how glass responds to the polishing tool, and in the latter decades of the 19th century, no workshop in America produced finer instruments than that of John Brashear in Pittsburgh. Brashear had begun as a millwright with a passion for astronomy, grinding his first telescope mirror in a shed behind his home, teaching himself the art through patient experimentation and correspondence with established opticians. His early efforts met with heartbreak, as one promising mirror cracked during the silvering process, but he persevered, and by the 1880s his reputation for excellence had spread throughout the astronomical community. The Brashear workshop, eventually housed in a proper factory on the south side of Pittsburgh, produced lenses and mirrors for observatories across the country and around the world. The spectroscopes that analyzed starlight at Allegheny Observatory, the optical components that helped Lick Observatory probe the heavens, the precision gratings and auxiliary instruments that enabled countless discoveries. Many of these emerged from Brashier's careful hands and those of the skilled craftsmen he trained. His work combined scientific understanding with artisanal skill, and his instruments were renowned not only for their optical quality but for the mechanical elegance of their mountings and adjustments. While the telescope gathered light and brought it to a focus, the recording of that light was undergoing its own quiet transformation during the same period. The astronomers of the mid-19th century had experimented with photography almost from the moment of its invention, but the early photographic processes were cumbersome and slow, poorly suited to capturing the faint light of stars and nebulae. The wet collodion process, which dominated photography in the 1860s and 70s, required the photographer to coat a glass plate with a sticky emulsion just before exposure and to develop it while the emulsion was still moist, a procedure that was awkward enough in a studio and nearly impossible in the cold and dark of an observatory dome. An astronomer wishing to photograph the sky had to prepare each plate individually, expose it while the collodion remained workable, and then hurry to develop it before the emulsion dried, all while guiding the telescope to compensate for the rotation of the Earth. The gelatin dry plate, which became widely available in the 1880s, swept away these inconveniences. The new plates came ready-made from the factory, coated with a silver halide emulsion suspended in gelatin that remained sensitive indefinitely, and they could be developed at the astronomer's leisure after the night's observations were complete. The dry plates were also more sensitive than their wet collodion predecessors, requiring shorter exposures to capture the same amount of light, and their sensitivity could be further enhanced through various techniques of hypersensitization. Astronomers discovered that bathing the plates in dilute ammonia before use, or exposing them briefly to hydrogen gas, or subjecting them to other chemical treatments, could increase their response to faint light, allowing ever longer exposures to reveal ever fainter objects. The photographic plate became the astronomer's most valuable ally, an impartial recorder that accumulated light over hours of exposure, capturing details too faint for the human eye to perceive, and it transformed astronomy from a visual science into an archival one, creating permanent records that could be measured and remeasured for generations to come. The light gathered by a telescope carries within it not merely an image but a story, encoded in the particular wavelengths that are present or absent, and the development of spectroscopy allowed astronomers to read that story with increasing fluency. The objective prism, a simple wedge of glass placed in front of the telescope's lens or mirror, spread the light of every star in the field into a small spectrum, allowing surveys of thousands of stars to be completed in a single night. At Harvard Observatory, under the direction of Edward Pickering, teams of women computers examined plate after plate of objective prism spectra, classifying stars by the patterns of dark lines that crossed their rainbow strips of light. The slit spectrograph offered higher resolution at the cost of observing only one star at a time, passing the starlight through a narrow opening before dispersing it, producing spectra sharp enough to measure the precise wavelengths of individual spectral lines, and thus to determine the velocities of stars through the Doppler effect, their chemical compositions, their temperatures, and eventually their distances. The quality of spectroscopic work depended critically upon the device used to disperse the light, and here the contributions of Henry Rowland at Johns Hopkins University proved transformative. Rowland developed methods for ruling diffraction gratings of unprecedented precision, using a dividing engine of his own design to cut thousands of parallel grooves into a polished metal surface, each groove separated from its neighbors by distances measured in thousandths of a millimeter. These Roland gratings, as they came to be known, spread light into spectra far purer and more detailed than any prism could achieve, and they became essential tools in astrophysical laboratories and observatories around the world. The spectra they produced revealed the universe as a vast chemical laboratory, filled with the same elements found on Earth but existing under conditions of temperature and pressure impossible to reproduce in any terrestrial furnace. George Willis Ritchie, working first at Yerkes Observatory and later at Mount Wilson, brought a perfectionist's eye to both telescope design and astrophotography. His innovations in the figuring of large mirrors pushed the art to new levels of precision, and his photographs of nebulae and galaxies, taken with instruments of his own design, revealed structural details that had never before been seen. Ritchie understood that the telescope and the camera were parts of a single system, and he worked to optimize every component, from the curvature of the mirror to the flatness of the photographic plate to the guiding mechanisms that held the image steady during long exposures. His later work on the Ritchie-Crétin optical design, developed in collaboration with the French astronomer Henri Crétin, offered a configuration free from certain optical aberrations that had plagued earlier reflectors, though the full adoption of this design would come only in later decades. Not all astronomical light falls within the narrow band of wavelengths visible to human eyes, and in the early 20th century a few pioneers began to explore the infrared radiation that lies just beyond the red end of the spectrum. William Koblenz, working at the National Bureau of Standards, adapted instruments called thermocouples and bolometers to detect this invisible heat radiation from celestial sources. A thermocouple measured temperature by the tiny electrical voltage produced when two different metals were joined and exposed to heat, while a bolometer detected radiation through the change in electrical resistance of a thin strip of metal as it warmed. These instruments were exquisitely sensitive but also frustratingly difficult to use, requiring careful shielding from stray heat sources and long integration times to detect the feeble infrared glow of stars. Koblenz measured the infrared brightness of the Moon and the brighter stars, laying the foundations for a branch of astronomy that would flourish only with the development of more sensitive detectors many years later. As photographic surveys grew more ambitious, astronomers found that the optical designs of traditional telescopes limited the area of sky that could be captured sharply on a single plate. The standard reflector designs produced good images only near the center of the field, with stars at the edges appearing stretched or blurred by optical aberrations. Frank Ross, working at Yerkes Observatory in the 1930s, developed corrector lenses that could be placed near the focal plane of a reflector to compensate for these aberrations, producing sharp images across a much wider field of view. These Ross correctors made survey photography practical on a new scale, allowing astronomers to photograph large swaths of sky with the efficiency needed to map the positions and brightnesses of millions of stars. And so, through decades of patient refinement, the instruments of the Mountaintop observatories grew ever more capable, each advance building upon those that had come before, each improvement opening new windows onto the universe. The work was rarely glamorous, often tedious, conducted in workshops and laboratories far from the public eye, but it was this work that made possible the great discoveries for which the observatories became famous. The grinding of a mirror, the silvering of its surface, the coating of a photographic plate, the ruling of a diffraction grating. These quiet labors were the foundation upon which modern astronomy was built, and they deserve to be remembered with gratitude by all who have marveled at the images and spectra that they made possible. The story of the 200-inch telescope at Palomar Mountain begins, as so many great astronomical endeavors do, with the restless imagination of George Ellery Hale, that same gentleman who had already given the world the 40-inch refractor at Yerkes and the 60-inch and 100-inch reflectors at Mount Wilson. By the late 1920s, Hale was in his 60s and in declining health, troubled by headaches and periods of nervous exhaustion that had plagued him throughout his adult life. Yet his mind continued to reach toward ever larger instruments, ever greater light-gathering power, ever deeper views into the cosmos. The 100-inch Hooker telescope had been in operation for nearly a decade by then, and while it remained the most powerful astronomical instrument on Earth, Hale understood that the questions astronomers were beginning to ask about the nature of galaxies and the scale of the universe would eventually require something grander still. In 1928, Hale began the delicate work of securing funding for what would become the largest telescope ever constructed, a reflector with a mirror 200 inches in diameter, which is to say 16 feet and 8 inches across, a disk of glass that would weigh many tons and gather 4 times the light of the Hooker telescope. He approached the Rockefeller Foundation with a proposal that was remarkable both for its scientific ambition and its estimated cost, requesting $6 million at a time when such sums were rarely devoted to pure scientific research. The negotiations proceeded through meetings and correspondence over several months, with Hale presenting his case for the scientific value of such an instrument, and the Foundation's trustees weighing the merits of so substantial an investment. In the autumn of that year, the Rockefeller Foundation agreed to provide the full $6 million, a grant that would fund not only the telescope itself but also the observatory buildings, the dome, the auxiliary instruments, and the mountain road that would be required to reach the chosen site. The site selection process considered several mountains in Southern California before settling on Palomar Mountain, a broad summit rising to nearly 6,000 feet above sea level in San Diego County, some 90 miles southeast of the California Institute of Technology, which would oversee the project. Palomar offered dark skies, steady air, and sufficient flat ground at its summit for the construction of a large dome, though reaching it would require the building of a new road capable of carrying extraordinarily heavy and delicate cargo. The first great technical challenge was the mirror itself, and here the project encountered difficulties that would delay progress for years. Hale and his colleagues initially hoped to cast the mirror from fused quartz, a material with an extremely low coefficient of thermal expansion, meaning it would change shape very little as temperatures rose and fell during the night. The General Electric Company undertook experiments to produce a fused quartz disk of the required size, attempting to build up the mirror by welding together smaller pieces of quartz in a laborious process that consumed years of effort and considerable expense. By 1931, however, it had become clear that the fused quartz approach was not succeeding, as the company struggled to produce disks of even modest size without flaws and cracks, and the project leaders reluctantly concluded that they must seek an alternative material. The alternative came in the form of Pyrex, a borosilicate glass developed by the Corning Glass Works of Corning, New York, which possessed a thermal expansion coefficient roughly 1/3 that of ordinary glass. While not as thermally stable as fused quartz, Pyrex could be cast using more conventional techniques, and Corning's engineers expressed confidence that they could produce a disk of the necessary dimensions. The mirror was designed with a ribbed honeycomb structure on its back surface rather than a solid slab, which would reduce the weight considerably while still providing the necessary rigidity, and this intricate pattern of ribs and pockets added greatly to the complexity of the casting process. In March of 1934, the Corning Glass Works attempted the first pour of the 200-inch disc, an event that attracted considerable public attention and drew crowds of onlookers to the factory in upstate New York. The process involved heating some 65 tons of raw materials in a special furnace and then allowing the molten glass, glowing a deep orange-red at its temperature of nearly 1500 degrees Celsius, to flow into an enormous ceramic mold that contained the cores which would form the honeycomb pattern. Workers and engineers watched anxiously as the pour proceeded, the glass filling the mold over a period of several hours, while the heat radiating from the furnace made the observation platforms almost unbearably warm. When the pour was complete and the long cooling process began, however, it became apparent that something had gone wrong, as several of the ceramic cores had broken free from their positions and floated upward into the body of the disk, creating flaws that rendered the mirror unusable for its intended purpose. This first disk, though a failure for astronomical purposes, was not discarded entirely, as it would later serve as a test piece for the grinding and polishing machinery. The Corning engineers studied the failure carefully and redesigned the mold to anchor the cores more securely, and in December of 1934 they attempted a second pour. This time the process proceeded without incident, the molten glass filling the mold properly and the cores remaining in their intended positions, and when the pour was complete the disk began its long and extraordinarily gradual cooling, the annealing process, during which the glass must cool slowly and evenly to relieve internal stresses that would otherwise cause it to crack or distort, required 11 months to complete, with the temperature of the annealing oven being reduced by only a fraction of a degree each day. Not until the autumn of 1935 was the disk cool enough to be removed from its mold and inspected, and the inspection revealed a successful casting, a disk of Pyrex glass 27 inches thick at its edge, weighing approximately 14.5 tons, ready to begin its journey westward. The shipment of the disk from Corning to California became something of a national event, capturing the imagination of a public still suffering through the depths of the Great Depression. The disk was loaded onto a specially designed railroad car equipped with elaborate shock-absorbing mechanisms to protect it from the vibrations and jolts of rail travel, and it left Corning on March 26, 1936. Beginning a journey that would cover more than 3,000 miles at speeds never exceeding 25 miles per hour. The route took the train through major cities including Philadelphia, Indianapolis, Kansas City, and Los Angeles, and at each stop crowds gathered along the tracks to catch a glimpse of the giant glass disk, this marvel of American engineering and craftsmanship that seemed to promise a future of scientific wonder. The journey required 16 days to complete, with the train arriving in Pasadena on April 10th, where the disk would remain for more than a decade, while the grinding and polishing work transformed its rough surface into a precision optical instrument. The work of figuring the mirror, which is to say the grinding and polishing of its surface to the precise parabolic curve required to focus starlight, was performed in a specially constructed optical shop at the California Institute of Technology under the supervision of Marcus Brown, a master optician of exceptional skill and patience. The process began with the rough grinding of the mirror using progressively finer abrasives to remove material and shape the general curve, followed by years of meticulous polishing and testing to achieve the final figure. The work required the constant measurement of the mirror surface using optical tests that could detect deviations of only a few millionths of an inch, and any errors discovered through testing had to be corrected by additional polishing in precisely the right locations. Marcus Brown and his team worked on the mirror throughout the late 1930s, but the entry of the United States into the Second World War in December of 1941 brought the project to a halt, as the nation's scientific and industrial resources were redirected toward the war effort, and the mirror was placed in storage for the duration of the conflict. During these years of waiting, significant work continued on other aspects of the project, including the design of the telescope mounting and the observatory building. Russell Porter, an artist, explorer, and amateur telescope maker of considerable renown, joined the project and contributed extensively to both the architectural design of the observatory dome and the mechanical design of the telescope itself, producing beautiful and precise drawings that helped engineers visualize the complex systems they were creating. Porter's cutaway illustrations of the telescope and dome became iconic images of the project, revealing the intricate machinery hidden within the great white structure. The telescope mounting was designed by Mark Serurier, a structural engineer who developed an elegant solution to the problem of supporting and moving so massive an instrument while maintaining the precise alignment of its optical components. The Serurier truss, as it came to be known, used a framework of steel tubes arranged in a configuration that minimized flexure and kept the mirror and the secondary optics properly aligned regardless of where the telescope was pointing in the sky. The complete mounting, including the yoke that supports the telescope tube and allows it to pivot in declination, while the entire assembly rotates in right ascension to track the stars, weighed approximately 134 tons. Yet was balanced so precisely that it could be moved by motors of only modest power. When the war ended in 1945, work resumed on the mirror figuring, and by 1947 the surface had been polished to within a few millionths of an inch of its intended curve across its entire 16-foot diameter. The transportation of the finished mirror from Pasadena to Palomar Mountain presented its own challenges, as the disc had to travel over public highways and then up the narrow winding road that climbed the mountain slopes. A specially designed trailer carried the mirror on a journey that required a full day to complete, with the truck proceeding at walking pace around the sharpest curves and crews of workers standing ready to clear any obstacles from the road. Onlookers gathered at various points along the route to watch the great disc pass, this eye of glass that would soon look deeper into the universe than any instrument before it. The installation of the mirror in its cell at the base of the telescope tube, the alignment of the optical system, and the final testing of all the mechanical and electrical systems occupied the latter months of 1948 and the early weeks of 1949. On January 26, 1949, the telescope achieved first light, that moment when an astronomical instrument is first pointed at the sky and captures its initial images, confirming that all its systems are functioning and that the years of design and construction have resulted in a working observatory. The formal dedication of the telescope took place on June 3, 1948, some months before first light, when the observatory was named the Hale Telescope in honor of George Ellery Hale, who had passed away in 1938, a decade before seeing his final and greatest instrument completed. Hale had lived long enough to see the mirror successfully cast and to know that his vision would eventually be realized, but he did not live to see starlight focused by the great glass disc he had worked so hard to bring into being. The dedication ceremony brought together astronomers, engineers, and dignitaries who spoke of Hale's contributions to astronomy and of the discoveries that the new telescope would surely make in the years and decades ahead. The Hale telescope remained the largest optical telescope in the world for nearly half a century, from its completion in 1949 until the construction of larger instruments in the 1990s. And during that time it contributed to countless discoveries about the nature of galaxies, quasars, the expansion of the universe, and the chemical composition of distant stars. The 200-inch mirror, that disc of Pyrex glass poured in a factory in upstate New York and transported across a continent by train and truck, continues to gather starlight on its mountaintop to this day, a testament to the ambition, patience, and craftsmanship of all those who brought it into being across 2 decades of effort. Life above the clouds, on the great observatory mountains of the American West, was shaped not only by the demands of astronomical research but by the simple facts of geography, weather, and human endurance. The men and women who lived and worked at places like Mount Wilson, Mount Hamilton, and later Mount Palomar inhabited communities unlike any others, perched thousands of feet above the valleys where ordinary life went on, separated from towns and cities by winding mountain roads that could become impassable for days or even weeks at a time. Their daily existence was governed by rhythms that inverted the normal patterns of human activity, and they developed customs and routines suited to the peculiar circumstances of their remote and elevated homes. To understand the history of mountaintop astronomy is to understand not only the telescopes and the discoveries they enabled, but also the texture of ordinary days lived in extraordinary places, where the boundary between the professional and the domestic was often very thin indeed. The fundamental fact of observatory life was that astronomers worked through the night and slept through the day, a schedule that placed them permanently out of phase with the rest of humanity. A typical observer might rise in the late afternoon, when the sun was already beginning to sink toward the Pacific, and take a light meal before beginning preparations for the night's work. The great dome would be opened, the telescope cooled to match the temperature of the air, and photographic plates or other instruments made ready. As darkness fell, the work would begin in earnest, and it might continue without interruption until the first light of dawn began to wash the eastern sky. During the long night hours, the observer would guide the telescope, adjust instruments, change plates, and keep careful records, often working in near total darkness to preserve the sensitivity of the photographic emulsions and the adaptation of one's eyes. Coffee was a constant companion, and meals might be taken at any hour, brought to the dome by a cook or fetched during brief intervals when the telescope could be left to track on its own. At Mount Wilson, the living arrangements reflected both the practical necessities of remote mountain life and the social conventions of the era. The main residential building was known informally as the monastery, a name that captured something of its austere character and also its most notable rule, which was that women were not permitted to stay overnight. This was not merely a matter of custom but of official policy, one that would seem remarkable to later generations but was largely unremarked upon at the time. The monastery was a substantial building of stone and wood, comfortable enough in its way, with bedrooms for the resident astronomers, a common dining room, and a sitting room where men might read or converse during their daytime hours of rest. The atmosphere was said to be collegial and quiet, with conversation tending toward the scientific but occasionally straying into philosophy, literature, or the small concerns of daily life. Meals were prepared by dedicated cooks who understood the peculiar schedules of their charges and who were accustomed to serving breakfast at 3 in the afternoon or dinner at midnight. Visitors to Mount Wilson, particularly those who brought wives or families, were accommodated at Kaptein Cottage, named for the Dutch astronomer Jacobus Kaptein, who had spent productive periods working on the mountain. Kaptein Cottage offered somewhat more domestic arrangements and was one of the few places on the mountain where women could stay, though their presence was still governed by careful protocols. The international character of the observatory's visitors was evident even in these early decades, as astronomers from Europe and elsewhere made the long journey to use instruments that were, for their time, unmatched anywhere in the world. The cottage became a kind of way station for the global community of astronomers, a place where Dutch and English and German voices might mingle with American ones, discussing the same stars and nebulae that could be seen so clearly from the California peaks. The isolation of these mountain observatories was romantic in the abstract but often quite difficult in practice, particularly during winter months when storms could cut off access for extended periods. At Mount Hamilton, Home of the Lick Observatory, the single road connecting the summit to the valley below was prone to becoming impassable when snow or rain made the steep grades treacherous. There were winters when the observatory community found itself entirely cut off from the outside world, dependent on whatever supplies had been laid in before the storms arrived. Food shortages were not unknown, and careful planning was required to ensure that the essential provisions, flour and coffee and canned goods and fuel, were sufficient to last through prolonged isolation. Water lines froze, requiring laborious thawing or the hauling of water by hand from whatever sources remained liquid. The observatory's small community drew closer together during these times, sharing meals and resources and the particular fellowship that comes from weathering hardship in company. The same isolation that made winters difficult also created certain dangers, and none was more feared than fire. In the autumn of 1913, Mount Wilson faced this threat in a particularly direct way when a wildfire, driven by the hot, dry winds that sweep through Southern California, advanced toward the observatory. The flames moved through the brush and chaparral on the lower slopes, climbing toward the summit where the great 60-inch reflector and the solar telescope stood. For a time, it seemed possible that the entire installation might be lost, along with years of work and irreplaceable instruments. The observatory staff, joined by firefighters who had made their way up the mountain road, fought to protect the buildings and domes, and in the end they succeeded, though not without considerable effort and anxiety. The fire passed, leaving scorched earth on the slopes below but sparing the structures on the summit. This near disaster served as a reminder of the vulnerability of these remote installations and led to improved fire preparedness in the years that followed. Daily life on the mountain was not entirely given over to work and worry. The communities that formed around these observatories developed their own forms of recreation, suited to the geography and the temperament of their members. At the Lick Observatory, a tennis court had been constructed on a rare flat stretch of ground, and astronomers who had been awake all night might play a set or two in the afternoon before retiring to bed. The exercise was said to be beneficial for both body and mind, and the court became a gathering place where scientific discussions might continue in a more informal setting. At Mount Wilson, a hiking club was established, and those who were not too exhausted by their nocturnal labors might spend their free hours exploring the trails that wound through the surrounding mountains. The San Gabriel Range offered abundant opportunities for such excursions, and the astronomers came to know the local peaks and canyons with an intimacy born of repeated visits. Amateur dramatics were another form of entertainment, with the observatory community occasionally staging theatrical productions for their own amusement. These performances were modest affairs, sometimes little more than readings or skits, but they provided a welcome diversion from the routines of scientific work and the monotony that could settle over a small, isolated community. The casts were drawn from the available personnel, astronomers and technicians and cooks taking on roles for which they had no particular training but considerable enthusiasm. The audiences were equally informal, consisting of whoever happened to be on the mountain and not engaged in observations. These small pleasures, tennis and hiking and amateur theatricals, served to bind the community together and to make the long periods of isolation more bearable. The administrative challenges of running a remote observatory were considerable. Everything required more effort than it would have in a town or city. Supplies had to be transported up the mountain road, sometimes by mule team in the earlier years, later by truck when the roads had been improved. Equipment that broke down could not be easily repaired, and specialized parts might take weeks to arrive. Staff had to be recruited who were willing to live under unusual conditions, and their welfare had to be attended to in ways that would not have been necessary in a more conventional workplace. The director of such an observatory was as much a manager of a small village as a leader of scientific research, responsible for the housing and feeding and general contentment of all who lived and worked under his supervision. Budgets were always tight, and the competition for funding required constant attention, as did the relationships with the sponsoring institutions and the broader astronomical community. The Second World War brought unique circumstances to Mount Wilson, and one of the most poignant stories of that era concerns Walter Baade, a German astronomer who had come to the United States in the 1930s. When the war began, Baade found himself in an unusual position. As a German national, he was classified as an enemy alien, which meant that he was not eligible for military service and was in fact subject to certain restrictions on his movements and activities. At the same time, many of his American colleagues were leaving the observatory to serve in the armed forces or to contribute to the war effort in various scientific capacities. The mountain grew quieter, the staff reduced to a skeleton crew, and Baade, paradoxically, found himself with more access to the great telescopes than he had ever enjoyed before. He made remarkable use of this opportunity, conducting observations that would lead to fundamental advances in our understanding of stellar populations and the scale of the universe. There was something bittersweet in his situation, working alone on the dark mountain while the world below was consumed by conflict. His colleagues scattered to military installations and laboratories. The night sky above California blacked out by the dimming of city lights as a precaution against air raids. The very darkness that had been imposed for reasons of war improved the observing conditions, and Baade, an astronomer of great skill and patience, seized the chance that circumstances had given him. The international character of the observatory communities was evident throughout this period, even when travel was difficult and political tensions ran high. Jan Oort, the Dutch astronomer who would become one of the most important figures in the study of galactic structure, made several visits to Mount Wilson and other American observatories. His journeys from Holland were long and not without difficulty, particularly during and after the war, but the scientific connections that these visits fostered were invaluable. Oort brought with him perspectives and techniques developed in the European tradition, and he took back to Leiden ideas and data that enriched the work of his own institution. The mountaintops of California became, in this way, meeting places for a global community of scholars, united by their shared interest in the stars and their willingness to endure the inconveniences of remote mountain life in pursuit of knowledge. Visiting astronomers often found the experience of working at Mount Wilson or Lick to be both exhilarating and exhausting. The altitude took some adjustment, and the inverted schedule of sleeping by day and working by night was disorienting for those unaccustomed to it. The food was plain but sufficient, the accommodations comfortable but not luxurious, and the company was that of fellow scientists, earnest and intelligent but not always socially varied. Yet there was compensation in the quality of the skies, the power of the instruments, and the sense of participating in something larger than oneself. The great observatories were not merely workplaces but communities, small and sometimes eccentric, bound together by shared purpose and shared hardship. The daily existence on these mountains, with its odd hours and its isolation and its quiet pleasures, was the foundation upon which the great discoveries of the era were built, and it shaped the lives of all who passed through in ways that often stayed with them long after they had descended again to the valleys below. The stars wheeled overhead, season after season, and the observers kept their patient watch, recording what they saw and contributing, each in their own small way, to the slow accumulation of human understanding.